Hello there and welcome to Just About Earth, where curiosity gets comfortable and science takes its time. Tonight we're heading somewhere that sounds less like a place on our own planet and more like something a novelist would invent after too much coffee and not quite enough sleep. Deep beneath Romania, tucked away from sunlight, weather, seasons, and the ordinary fuss of the surface, there is a cave where life has been carrying on in near isolation for millions of years. No forests above it matter much. No sunrise reaches it. No leaf litter drifts politely down to feed the food chain. It is cut off, chemical, airless by our standards, and yet very much alive. Which is really quite rude if you think about it, because most of us struggle to keep a houseplant going near a window. Before we make our way down, I'd love to know where in the world you're listening from tonight, and what sort of hour it is in your little corner of things. Late evening, very early morning, one of those odd in-between times when the house is quiet but your thoughts are not. If you find this gentle descent soothing, intriguing, or simply a pleasant way to let the day loosen its grip, a like and a subscription would help this quiet little corner reach other listeners who might enjoy a calmer kind of science. And now let's ease our way toward one of the strangest hidden ecosystems ever found, because somewhere near the Black Sea coast, below ordinary roads and ordinary soil, there is a sealed world that seems to have ignored the usual rules for a very long time. Movile Cave does not announce itself with a dramatic cliff face, or a gaping entrance in the side of a mountain. In fact, one of the first unsettling things about it is how untheatrical its discovery was. It sits on the outskirts of Mangalia in southeastern Romania, only a few kilometres from the Black Sea, and for most of human history no one knew it was there. There was no natural opening to the surface, no cool cave breeze, no flock of bats providing a helpful hint. It was intercepted in June 1986 when an artificial shaft was dug during geological survey work. Imagine that for a moment. One day you're carrying out what seems like fairly ordinary field work, and the next you have opened a route into a subterranean system unlike anything anyone had properly documented on land before. Not simply a cave with some unusual minerals or a few pale insects, but access to a larger isolated ecosystem associated with a sulphurous aquifer. That is the sort of discovery that makes the phrase interesting site conditions feel hilariously inadequate. It is also part of what gives Movile Cave its hold on the imagination. It was not a place people wandered into by torchlight centuries ago. It was hidden, sealed away, and then suddenly, quite late in the story of modern science, it was there, waiting in the dark as if it had no particular intention of introducing itself at all. And what a place it turned out to be. Most caves, even the very remote ones, are tied to the surface in some way. Water percolates down, organic matter drifts in, air exchanges, tiny subsidies from the world above keep things going. Movile is different. Researchers describe it as the first terrestrial self-sustained ecosystem, dependent on chemosynthesis ever discovered, which is a very scientific way of saying that the whole arrangement runs on chemistry instead of sunlight. On the surface, life is accustomed to photosynthesis doing the heavy lifting. Plants and algae catch light, build organic matter, and everything else more or less joins the queue. But in Movile Cave there is no sunlight to begin with, and no routine delivery of food from above to keep the pantry stocked. Instead, microorganisms use chemicals supplied by deep thermomineral waters, including hydrogen sulfide, methane and ammonium, to produce the organic matter that supports the rest of the ecosystem. So when people call it an alien world, they are not merely being dramatic for effect. The base of the food web really is built in a way that feels more like a deep-sea hydrothermal vent than the caves most of us picture, with stalactites, tourist railings, and someone inevitably asking whether it's safe to lick the walls. Here, the answer to that last question is very much no. And perhaps also please reevaluate your choices. The cave itself is not immense in the way people often expect from legendary places. It is not some endless underworld stretching to the horizon. The known passages total roughly 240 metres, arranged as a horizontal maze with two levels, an upper dry section, and a lower portion that is partially flooded. And yet small does not mean simple. Some of the most important places in science are not grand in scale, but strange in principle. In Movile Cave, what matters is not size so much as circumstance. Warm air, high humidity, unusual chemistry, and zones where oxygen drops to levels that would make the average visitor deeply unhappy, all combine to create an environment that feels hostile before you even start describing the residents. In the upper level, the air is already unusual, while in the lower chambers and the so-called air bells, oxygen can fall to around 7%, and carbon dioxide rises sharply. The water becomes anoxic almost immediately below the surface in certain areas, and the atmosphere is rich in compounds that do not generally inspire confidence, especially hydrogen sulfide. It is the sort of setting where, if someone cheerfully told you they were arranging a guided weekend excursion, you would be well within your rights to stay home and reorganize a drawer instead. The cave is strictly protected, access is tightly controlled, and with good reason. This is not only a difficult environment for humans, it is also an extraordinarily delicate one. What makes the place even more striking is the depth of its separation. The ecosystem associated with Movile Cave is understood to have been isolated from the surface for around 5.5 million years, with researchers linking its history to geological events reaching back to the late Miocene. That kind of timescale has a way of rearranging your sense of what hidden really means. We use the phrase out of sight all the time for things mislaid in a cupboard, or forgotten in the back of a freezer. But this is concealment operating on geological patience. While climates shifted above ground, coastlines changed, and human history had not even begun to rehearse its first scene. This system remained cut off, chemical, stable in its own odd way, and quietly selective about who got to survive there. The result is an ecosystem famous for endemic life, species found there and nowhere else, with recent reviews describing more than 50 invertebrate species in the cave system, and well over 30 endemic forms depending on how the wider associated aquifer is counted. Many of them show classic cave adaptations such as loss of eyes, lack of pigment, and elongated limbs or antennae. That detail always lands with a certain chill. It means this is not simply life enduring in the dark for a while. It is life shaped by darkness for so long that darkness has become ordinary, expected, built into the body plan. Up above, sunrise is a certainty. Down there, sunrise is not part of the design brief. There is also something wonderfully unsettling about the idea that the engine of this ecosystem is not hidden somewhere deep in the rock as an abstract process, but visible in the form of microbial films and mats. In parts of the cave, especially in the air bells, the surface of the water can be covered by a floating microbial pellicle, thick enough in places to be described almost as a film or scum, held afloat by gas bubbles. This biofilm is not a side detail. It is the centre of the whole affair. It is the food source, the habitat, the productive base that makes everything else possible. Protists, nematodes, rotifers, crustaceans, snails, worms, predators higher up the chain, all of them are tied back to those microbial communities and the strange chemistry that feeds them. That, to me, is where Movile Cave stops being merely unusual and becomes deeply instructive. It forces a small correction in the way many of us picture life as a green and sunlit business. We are so used to leaves, roots, meadows, plankton lit from above, and the daily generosity of the sun that a chemically powered ecosystem underground feels almost like a loophole. Yet it is not a loophole at all. It is life doing what life does when the ordinary options are removed. It improvises, specialises, narrows, adapts, and carries on with a seriousness that is almost comical when compared with our own tendency to declare a day ruined because the Wi-Fi has become temperamental. Of course, there is a reason this cave so often appears in science writing with a tone of disbelief. The disbelief is earned. From the surface, it is hard enough to imagine living without daylight. Harder still to imagine a functioning community in warm, humid, low oxygen chambers where toxic compounds are not accidental contaminants, but part of the basic setting. And yet the record from Movile Cave shows not only survival, but complexity. Reviews of the system describe aquatic and terrestrial communities, with consumers feeding on microbial production and predators feeding on them in turn. Water scorpions, leeches, spiders, centipedes, isopods, millipedes, worms, crustaceans, all participating in a food web that would sound impossible if it were pitched in a meeting as a speculative screenplay. You can see why scientists took such notice. Before Movile, chemosynthesis-based ecosystems were known from places like deep-sea hydrothermal vents, but here was a terrestrial groundwater system running on similar logic. That matters not just because it is unusual, but because unusual systems teach us where the edges of the possible really are. Every time biology finds a way to flourish in conditions we would have dismissed as absurd, it broadens the definition of habitable and makes our old certainties look slightly provincial. The surface world begins to seem less like the standard model for life and more like one successful arrangement among several. There is another reason the cave lingers in the mind, and it has less to do with chemistry than with mood. We tend to think of sealed places as dead places. A locked room, a buried chamber, a system cut off from air and light for immense spans of time. All of these suggest stillness, emptiness, preservation at best. Perhaps a few minerals, perhaps some stale air, perhaps a sort of silence that museums would label do not touch. Movile Cave breaks that expectation in a particularly stubborn way. It is sealed, yes. It is difficult, yes. But it is not still in the sense we usually mean. It is busy at microbial scale, busy chemically, busy evolutionarily. It has been a place of ongoing processes for millions of years while remaining almost completely outside human notice. That thought has a calming quality to it, oddly enough. Not cheerful exactly, but steadying. There are worlds within this world that do not require our attention in order to continue. Their clocks are not our clocks. Their conditions are not adjusted for our comfort. Their persistence does not ask for applause, it simply goes on. A cave near Mangalia, hidden below ground, has been quietly running a chemical economy of life while empires rose and fell on the surface, and while our species slowly taught itself how to name such things. There is something humbling in that, and perhaps something useful too, especially late at night when human concerns can begin to feel both oversized and oddly flimsy. So as we settle a little deeper into this story, it helps to leave behind the usual cave imagery. The adventurous caver, the beam of a headlamp, the neat geological labels, the sense that underground places are merely shadowed versions of the surface. Movile is not that. It is less like a basement and more like a separate negotiation with reality. The air is wrong by our standards. The water is wrong by our standards. The food chain begins in the wrong place by our standards. And yet all of those standards turn out to be negotiable. That is the real hook here. Not simply that the cave is strange, but that it quietly reminds us how narrow our everyday assumptions can be. We take sunlight as the beginning of everything because for most of the visible world around us, it is. We take fresh air as normal because our lungs have grown spoiled and opinionated. We take ecosystems to be open, linked, washed by weather, and fed by seasons. Then Movile Cave appears in the record and says, not loudly, but very firmly, that life can do something else. It can retreat underground, accept sulfur and methane instead of sunbeams, and spend millions of years becoming more itself in the dark. And before we meet the pale hunters, the blind crawlers, the microbial films, and the chemistry that keeps this place from becoming just another dead void in the limestone, it makes sense to begin with the hidden setting that allowed all of it to happen, because the cave's creatures are strange, certainly, but the world that made them strange is where the real story starts. When people hear about Movile Cave for the first time, they often imagine some dramatic opening in a cliff, perhaps hidden by ivy, with a current of cold air whispering out from the dark as if the earth itself were trying to tell you a secret. In reality, the setting is much less theatrical and somehow more unsettling because of it. Movile Cave lies in southeastern Romania, in the Dobrogea region, on the outskirts of Mangalia in Constanța County, only a few kilometres from the Black Sea coast. It sits at very low elevation, roughly 10 metres above sea level, in a landscape that does not look like the front door to one of the strangest ecosystems on Earth. There was no natural entrance inviting curious humans inside. The cave had no obvious mouth at the surface at all. It remained hidden beneath quaternary deposits and was only intercepted in June 1986 when an artificial geological survey shaft was dug. In other words, this was not a place that people gradually came to know. It was a sealed underground world that was quite literally stumbled into by modern investigation. That detail matters because it shapes the whole mood of the story. Movile was not just remote. It was inaccessible by ordinary means, which helps explain how an ecosystem could continue almost entirely outside human notice until very recently. It is still described as the only human accessible entrance to a much broader chemosynthesis-based ecosystem associated with the local sulfurous aquifer. That part of Romania has a geology that sounds technical on paper, but becomes easier to picture if you imagine layers of history stacked with no concern for our convenience. Southern Dobrogea belongs to the Moesian platform along the Black Sea coast, and the cave itself developed in Sarmatian limestones, roughly 12.5 million years old, which were later covered by younger clays and loess. The broader aquifer connected to Movile lies deeper in Mesozoic limestones, and the reduced chemical compounds that drive the cave's ecosystem rise upward along geological faults. This is one reason the cave is so interesting scientifically. It is not merely a hole in rock. It is a point of access to a deeper groundwater system with its own chemistry, circulation, and long isolation. Researchers describe the aquifer feeding the system as an artesian one at around 180 to 200 metres depth, supplying thermomineral water rich in hydrogen sulfide, methane, and ammonium. Those chemicals, which most of us would greet with concern rather than gratitude, are central to how the ecosystem functions. The cave also shows signs of sulfuric acid speleogenesis in combination with more classical karst dissolution, meaning that the cave was shaped not only by ordinary limestone dissolution, but also by chemical processes linked to sulfur oxidation. So the hidden world beneath Romania is not just biologically unusual, its very architecture is bound up with the same chemistry that later became the basis for life there. That is efficient in a rather unnerving sort of way. If you were able to stand at the shaft and descend into Movile Cave, what you would find is not a giant underground cathedral, but a comparatively compact labyrinth. The known cave is about 240 metres long and arranged as a horizontal maze with 2 levels. The upper level is dry, warm, and lacks the decorative stalactites and stalagmites that people often associate with caves. The lower level is partly flooded and includes the lake room and 3 so-called air bells, which are the only aerated zones in that section. This physical layout matters because it creates a cave that is not one single uniform environment, but a sequence of increasingly strange compartments. In the upper level, the atmosphere is already unusual, recorded at around 21 degrees Celsius, with about 19% oxygen and around 1% carbon dioxide. Those figures are not yet the sort that would make a scientist immediately sprint for the ladder, but they are a warning that things are headed in a less hospitable direction. Further down in the air bells, oxygen drops as low as 7%, while carbon dioxide rises to around 3.5%, largely because of microbial activity. The water itself becomes completely anoxic below just 1 millimetre in some zones. It is quite a talent, really, for a cave to manage the atmosphere of a badly ventilated argument, while simultaneously maintaining one of the most famous isolated ecosystems on land. The place where Movile sits is therefore important in 2 senses at once. Geographically, it is near the Black Sea, close to the surface, and on land that most people would not look at twice. Environmentally, though, it is connected to a hidden groundwater world that behaves according to very different rules from the one above it. The cave is often described as the hotspot of the sulphurous aquifer near Mangalia, and that phrase hotspot is useful because it reminds us that Movile is not the whole story by itself. It is the visible, or at least reachable, point in a larger system. UNESCO's tentative listing for the site describes it as the access gate to a self-sustained ecosystem associated with the thermal sulphurous aquifer. There are also sulphurous springs at the surface and submarine springs discharging in shallow water offshore, which offer glimpses of the same broader underground setting. So, while the cave became famous, the true hidden world beneath Romania is not confined to one corridor and one lake room. Movile is better understood as a window into a broader subterranean network shaped by geology, chemical inputs, and long-term isolation. That perspective helps explain why the discovery felt so important. Scientists had not merely found an odd cave, they had opened a route into a terrestrial chemosynthesis-based system that was already functioning before anyone knew it existed. It is the scientific equivalent of finding a door in your hallway and realizing it does not lead to a cupboard, but to an entirely different economy. One of the most striking parts of that hidden setting is how thoroughly it departs from the surface pattern most ecosystems follow. On the surface, food webs generally begin with sunlight. Plants, algae, cyanobacteria and other photosynthetic organisms capture light energy, and everything else feeds directly or indirectly on that productivity. In Movile Cave there is no sunlight at all, no regular input of leaf litter or surface debris to keep the system going, and yet the food web is both real and complex. Researchers describe Movile as the first subterranean groundwater ecosystem known to rely entirely on chemosynthesis. Microorganisms use energy from oxidizing hydrogen sulfide, methane and ammonium supplied by the deep thermal mineral waters. Those microorganisms, whether free-swimming or arranged in thick biofilms on water surfaces, cave walls and sediments, produce the organic matter that supports the rest of the ecosystem. This means the cave is not living off leftovers from above. It is making its own living in place, in the dark, by chemical means. Once you understand that, the landscape above starts to feel oddly irrelevant. A sunny day over Mangalia does not feed the cave. A cloudy one does not deprive it. Surface weather may matter for many things, but not for the fundamental energy budget of this ecosystem. That independence is one reason scientists so often compare Movile to deep-sea chemosynthetic systems, even though it lies beneath an ordinary corner of Romania rather than under kilometres of ocean. Isolation, of course, is the word that gives the cave its deeper hold on the imagination. The ecosystem associated with Movile is commonly linked to roughly 5.5 million years of separation from the outside world, and UNESCO's site description explicitly connects the cave's biological story with geological events including the Messinian crisis around 5.5 to 5.2 million years ago. That timescale is useful not merely because it sounds impressive, though it certainly does, but because it helps explain why the life there is so specialised. Over very long spans, underground colonists can become fully committed to the conditions they inhabit. Species lose pigment because colour is pointless in darkness. Eyes are reduced or disappear because there is nothing to see. Other senses and structures become more important. Limbs and antennae may lengthen. Behaviour shifts. Physiology shifts. The result is not simply a surface animal enduring cave life badly, but lineages that have been shaped by it. Recent reviews describe more than 50 invertebrate species in Movile Cave, with dozens of endemic species depending on the count and taxonomic updates used. The point is not the exact number so much as the pattern. A sealed or semi-sealed hidden world, supplied by unusual chemistry and cut off over geological time, has acted as an evolutionary workshop. It is one of those rare places where isolation is not a metaphor. It is a biological force with a very long memory. Because the cave stayed unknown for so long, the story of its discovery has an unusual texture. It does not belong to the age of romantic exploration, and it does not come with medieval rumours, local legends, or Victorian naturalists emerging from the dark covered in mud and enthusiasm. It was found in a modern context, during survey work linked to development, and then gradually recognised for what it was. The Romanian researcher Cristian Lascu is closely associated with the cave's early exploration and scientific documentation, but the important thing here is how quickly the site moved from curiosity to highly controlled research environment. Access is strictly regulated for protection reasons, and only a limited number of researchers are allowed inside. That is not academic fussiness, it is practical necessity. Human presence brings oxygen, microbes, heat, and disturbance. In a place where atmospheric chemistry is already unusual, and the ecosystem is both isolated and delicate, careless traffic would be disastrous. It is one of the few discoveries where the right response is not to build a visitor centre and print cheerful maps, but almost the opposite. The hidden world beneath Romania remains hidden in a very literal sense because keeping it intact depends on it. We often talk as though the highest compliment we can pay a remarkable place is to make it accessible. Movile Cave is a good reminder that sometimes the more respectful response is to leave a door mostly closed. There is also a useful correction in the way Movile changes how we picture subterranean life more generally. Many caves around the world contain specialised fauna, and many are biologically important, but most still receive some subsidy from the surface. Water washes in dissolved organic matter, roots penetrate from above, insects fall in and become lunch. The deeper story of Movile is that it demonstrates a far more independent model. The microorganisms there do not simply tidy up what the surface provides. They are primary producers in their own right. Their activity supports aquatic grazers, detritivores, and predators, and the terrestrial community is similarly tied into locally generated productivity. The review in Diversity describes the microbial biofilms as the food source for protists, rotifers, nematodes, gastropods, and crustaceans in the aquatic realm, while the terrestrial community includes worms, isopods, pseudoscorpions, spiders, centipedes, millipedes, springtails, diplurans, and beetles. That is not a token scattering of extremophils barely hanging on. It is a functioning community. A strange one, yes, and one nobody would nominate for a family picnic, but a functioning community all the same. Once that sinks in, the cave becomes less like an oddity and more like a lesson in how provincial our default picture of habitability can be. We tend to assume life requires what we require. Movile is what happens when biology declines that assumption and gets on with things. If we narrow the lens again and think simply about place, there is something almost comic in the contrast between surface normality and subterranean strangeness. Above ground near Mangalia, you're in southeastern Europe, near the coast, in a region with roads, settlements, weather, agriculture, and the ordinary signs of human geography. Below ground, the rules change so abruptly that the cave has often been described in language borrowed from astrobiology in extreme environments. Low oxygen, elevated carbon dioxide, hydrogen sulfide, methane, warm humid air, stagnant sulfidic water, microbial films at the water surface, and endemic blind invertebrates are not features we usually associate with a patch of land a short distance from the sea. Yet that is exactly why the location matters. It is not hidden in Antarctica or under a volcano, or in some cinematic desert no one visits. It is beneath a region people know and live in. That closeness makes the concealment more striking. The cave demonstrates that large scientific surprises do not always sit in remote blank spots on a map. Sometimes they are beneath familiar ground, waiting for the right shaft, the right measurements, and the right questions. There is something very healthy about that idea. It keeps science from becoming too smug. Just when we start behaving as if the world has been mostly catalogued, and the remaining mysteries are minor administrative details, a place like Movile appears and politely ruins that mood. So when we talk about the hidden world beneath Romania, we are really talking about a layered secret. There is the obvious hiddenness of the cave itself, buried and entranceless until modern work intercepted it. There is the geological hiddenness of the aquifer and faults feeding reduced chemicals upward through rock. There is the biological hiddenness of a food web that does not advertise itself with green leaves or birdsong, but with microbial films floating over toxic water. And then there is the historical hiddenness of a place that kept going for immense stretches of time while the surface remained unaware. That combination is what makes Movile Cave more than a curiosity. It is a setting where geology, chemistry and evolution all conspired to produce a world close to us in distance and very far from us in habit. And now that we have a clearer sense of where it is and what sort of underground realm it belongs to, the next thing worth lingering on is the atmosphere of the cave itself, because it is one thing to say that a hidden world exists beneath Romania, and another to understand what it actually means to stand at the edge of water you should not trust, in air your lungs would object to almost immediately, while life carries on as if all of that were perfectly ordinary. To understand Movile Cave properly, it helps to stop thinking of it first as a place full of unusual animals, and start thinking of it as a place with unusual air. That may sound like a slightly disappointing beginning, rather like being told the most interesting thing about a grand old library is the dust, but in this case the air really does deserve top billing. By ordinary human standards, the atmosphere in Movile Cave is wrong in several directions at once. In the upper level of the cave, researchers have recorded warm air at about 21 degrees Celsius, with oxygen around 19% and carbon dioxide up to roughly 1 to 1.5%. Deeper down, in the lower passages and especially in the air bells above the sulfidic water, the air becomes much more extreme, with oxygen dropping to around 7% while carbon dioxide rises to about 3.5%. Methane is also present, and the whole space is associated with hydrogen sulfide and ammonia-rich conditions. UNESCO site description notes that from the entrance onward, the smell of sulfur compounds is strong and becomes stronger toward the deeper part of the cave. So before you meet a single spider, snail or centipede, the cave has already introduced itself with a chemistry lesson that your lungs would very much prefer not to take. That shift in atmosphere matters because the cave is not merely stale or badly ventilated in the way an ordinary underground space might be. It is chemically active. The air is shaped by processes happening in the cave and in the deeper aquifer connected to it. Warm vapours rise from the sulfidic water in the lower level and move into the upper passages. Microbial activity contributes heavily to the carbon dioxide burden, and methane oxidation also plays a part. This is one reason the cave feels so self-contained and so inhospitable at the same time. It is not simply cut off from the surface and left to sit there. Its atmosphere is being continuously modified by the same chemical and biological processes that keep the ecosystem going. The result is a space where the air is less like neutral background and more like part of the machinery. On the surface, air is something we mostly ignore unless it is unusually hot, cold, smoky or full of pollen. In Movile Cave, the air is impossible to ignore because it is one of the defining conditions of the environment. It is not a medium life happens to occupy. It is part of the problem life has had to solve. Low oxygen is probably the easiest part for us to relate to, because we know immediately what it means in human terms. At sea level, ordinary atmospheric oxygen is about 21%. In parts of Movile Cave, especially the air bells, that figure falls to around 7%, with some descriptions of the cave environment giving a broader range of roughly 7 to 10% in the deeper sections. That is not a small dip. It is the kind of difference that turns air from an unexamined comfort into a limiting factor. Human visitors do not belong there in any casual sense. Access to the cave is highly restricted, and research visits are carefully managed not just to protect the ecosystem, but because the environment itself is genuinely hazardous. It is one thing to visit a cave where you need a helmet and a torch. It is another to enter a space where the air offers only a fraction of the oxygen your body expects while carbon dioxide and sulfide levels climb at the same time. That combination is why popular descriptions of Movile often use words like toxic, suffocating, or alien, and for once those are not merely there to add drama. the cave is physically hostile to us in a straightforward, practical way. Carbon dioxide deserves its own moment because it changes the feel of the cave in a way that is easy to underestimate. When most of us think about dangerous cave atmospheres, we picture lack of oxygen alone, as though the problem were simply emptiness. But Movile is not empty. It is crowded with gases that shift the chemistry and the bodily experience of being there. UNESCO's description notes carbon dioxide enrichment in the upper galleries up to 1.5%, while the air bells can reach around 3.5%. That is dramatically above ordinary outdoor air. The source is not mysterious in the sense of being supernatural, though the cave does have a talent for encouraging melodramatic thoughts. Carbon dioxide there comes from biological metabolism and from processes tied to methane oxidation. In other words, the cave is breathing in its own subterranean fashion, though I would not recommend saying that aloud while standing at the shaft unless you want everyone around you to look thoughtfully concerned. The elevated carbon dioxide also matters geologically, because when warm condensed water on the walls mixes with it, carbonic acid forms and contributes to corrosion of the limestone surfaces. In Movile Cave, the atmosphere is not only difficult for animals, it is also one of the things slowly reshaping the cave itself. Then there is hydrogen sulfide, which may be the chemical signature most people associate with the cave once they hear about it. Hydrogen sulfide is the compound that gives the smell of rotten eggs, and Movile Cave's deep waters are rich in it. The cave is repeatedly described in the scientific literature and by UNESCO as part of a sulfurous aquifer system, with water rich in hydrogen sulfide, methane and ammonium. In practical terms, hydrogen sulfide is not just a smell. It is one of the key reduced compounds that fuels the chemosynthetic microbial communities supporting the food web. But for human observers, it is also a constant sensory warning that this environment is not adjusted for our comfort. The smell becomes stronger toward the deeper parts of the cave, and the lower flooded level is specifically described as containing sulfide-rich water. It is always tempting, when hearing about an ecosystem powered by chemicals, to focus on the elegance of the process and forget the immediate physical reality. Yet this is not chemistry taking place politely in a flask. It is chemistry present in the air and water around you, enough to shape corrosion, support microbial growth, and create conditions that most surface-dwelling animals would find intolerable. The cave smells wrong because in a very real sense, it is built around compounds the surface world usually treats as warning signs. Methane adds another layer to this already rather discouraging brochure. Scientific reviews describe the cave atmosphere and waters as containing methane, often around 1 to 2% in the cave air, with the deeper groundwater and air bells closely tied to methane-rich conditions. Methane matters for at least two reasons. First, it is part of the chemical budget that supports microbial primary production, because methanotrophic bacteria can use it as an energy and carbon source. Second, in the air bells, it helps explain one of the cave's strangest visual details. The thick floating microbial pellicle at the water surface can be kept afloat by methane bubbles. That is the sort of sentence that makes Movile Cave sound as though it was designed by someone trying very hard to ensure normal tourism would never become an option. A floating microbial film supported by gas bubbles in low oxygen, air above sulfidic water, is not what most of us picture when we hear the phrase inland cave system, but there it is. The air again is not incidental. It interacts with the water surface, the microbes, and the ecosystem as a whole. Methane is both a fuel and a physical participant in the scene. It helps make the cave feel less like a static underground void and more like a chemically restless chamber where biological productivity and atmospheric conditions are tightly intertwined. If the air is the first warning, the water is the second and perhaps the more decisive one. The lower level of Movile Cave contains warm, sulfidic water, and researchers have shown that dissolved oxygen is measurable only in the first few centimetres below the surface. UNESCO's description says oxygen is present only in the first 5 centimetres, and that deeper than that, the water is anoxic. other summaries report very low dissolved oxygen right at the surface, dropping to less than 1 micromolar within just a few centimetres and becoming fully anoxic with increasing depth. That means the water is not merely stagnant in an ordinary sense, it is sharply stratified by chemistry. A thin skin near the top may hold enough oxygen to measure, but just below that, the conditions shift into a world with no dissolved oxygen at all. For most aquatic life as we know it, that is effectively an eviction notice. For the organisms of Movile Cave, it is simply the neighbourhood. Still, for a human reader, this is where the phrase, "water you shouldn't touch" starts to earn its keep. Warm, murky, sulphur-rich, low in oxygen, and chemically active is not the profile of water one regards with confidence. It is more the profile of water one regards from a respectful distance while congratulating the microbes on their career choices. The water is also tied to the cave's warmth and near saturation humidity. Popular descriptions and scientific sources alike note that the cave maintains a temperature of about 21 degrees Celsius and relative humidity close to 100%. The lower level is warmed by the thermal sulfide-rich water, and the resulting warm vapours rise through the passages. This matters because it makes the cave feel less like a cool rocky basement, and more like a chemically compromised greenhouse with no sunlight and very poor air management. The high humidity contributes to condensation on the walls and ceilings. That condensed water, enriched by dissolved gases, participates in further corrosion. UNESCO describes a difference between wall temperature and air temperature that leads to water condensation and carbonic acid formation, accelerating limestone dissolution, while sulfuric acid corrosion associated with hydrogen sulfide further modifies the rock. Gypsum crystals form where condensed water and sulfur chemistry meet. So even the dampness is not a passive inconvenience, it is geologically active. The walls are being worked on by the same atmosphere and water that define the cave's biological conditions. You could say the cave is humid in the same understated way one might say the open sea is a bit damp. Technically true, but not really sufficient. There is an important visual difference too between the lake room and the air bells, and it tells you a great deal about how fine-tuned the cave's chemistry is. UNESCO's description notes that in the air bells, but not in the lake room where oxygen is closer to normal, the water surface is covered by a microbial pellicle that can be up to 2 centimeters thick. Those surface films are made up of bacteria, archaea, and fungi, and serve as both habitat and food. The contrast is useful because it shows that small differences in oxygen availability and local conditions produce visibly different outcomes. This is not one homogeneous underground swamp where everything is equally miserable all the time. It is a mosaic of micro-environments. Some compartments hold somewhat more oxygen, others are heavily suboxic or anoxic. Some support thick floating films, others only thin loose surface layers. From a scientific point of view, that heterogeneity is part of what makes Movile so interesting. From a storytelling point of view, it means the cave is not simply deadly in a broad theatrical way, it is precise. Conditions vary over short distances, and those variations matter tremendously. That sort of precision is usually what makes extreme environments truly compelling. Not simply that they are harsh, but that they are structured. All of this raises a sensible question. Why describe the water as something you should not touch, when the more obvious problem seems to be breathing the air? Partly because the water and the air are not separate hazards. They are in conversation with one another. The reduced chemicals in the water feed microbial oxidation. The atmosphere supplies limited oxygen at interfaces, especially in the air bells. Methane bubbles help hold microbial films afloat. Condensation carries dissolved compounds onto cave walls. Hydrogen sulfide in the water contributes to sulfuric acid processes that alter the rock. In Movile Cave, the boundary between atmosphere and water is not a simple dividing line. It is one of the most active parts of the system. The surface of the water is where chemistry and biology visibly meet, and where some of the cave's most productive microbial communities are concentrated. That is why the water seems so central even in a story about the atmosphere. It is the source of much of the cave's chemical identity, and it is also where the cave's self-sustaining logic becomes hardest to miss. On the surface world, lakes and ponds often reflect the sky. In Movile Cave, the water reflects the chemistry below and the strange life working on top of it. What is perhaps most remarkable is not merely that the environment is dangerous to us, but that the cave's animals and microbes are not simply tolerating it in a desperate way. They are adapted to it. UNESCO notes that aquatic organisms in the cave can survive high hydrogen sulfide concentrations and very low oxygen or anoxic conditions. Studies of the microbial communities likewise emphasize that the cave hosts organisms adapted to low oxygen, methane-saturated, sulfur-rich conditions. This is one of those cases where the phrase extreme environment needs to be handled carefully, because extreme for whom is the real question. For a surface mammal with strong preferences about breathable air and chemically uninteresting water, Movile is extreme. For the cave's own communities, these are the settled conditions of home. That shift in perspective is one of the most useful things the cave offers. It reminds us that habitability is not a universal standard set by our comfort. It is a match between organism and environment. Humans would last in Movile Cave only with considerable care. The cave's native life, by contrast, has spent vast spans of time making these conditions ordinary. That is why the air feels so important in the story. It is not just dangerous, it is selective. It decides, along with the water, who belongs. There is also something quietly impressive about how stable these unpleasant conditions appear to be. We often imagine hostile environments as chaotic ones, full of sudden swings and dramatic violence. Movile is hostile, but much of its hostility is steady. The warm temperatures, high humidity, reduced oxygen, elevated carbon dioxide, sulfide-rich waters, and methane-linked processes create an environment that is harsh but persistent. Stability of that kind can be a gift to evolution. A difficult but long-lasting setting gives organisms time to specialize. It also gives scientists a rare chance to study what life does when the basic rules stay odd for a very long time. The cave's atmosphere is therefore not just an obstacle course. It is part of the historical continuity of the ecosystem. This is the air under which the cave's endemic species evolved. This is the water in which microbial production became the base of the food web. This is the chemistry that allowed Movile to become not simply a bizarre place, but a coherent one. And once you start looking at it that way, the cave stops feeling like a grim exception and starts feeling like a complete world with its own standards. Those standards just happen to be terrible by ours, so by the time a researcher reaches the lower sections of Movile Cave, the point has already been made without any animal needing to perform for the occasion. The air tells you this world was not built with mammals in mind. The water confirms it. Low oxygen, high carbon dioxide, sulfur compounds, methane, ammonium, warm vapor, thick humidity, anoxic depths, floating microbial films and rocks slowly altered by acid-forming condensate, all combine to create a place that feels less like an underground absence and more like a fully operating system that happens to exclude almost everything familiar. That is why Movile Cave leaves such a strong impression even before we start naming its inhabitants. The environment itself feels improbable, and yet improbability is not the same as impossibility, which is where the story becomes more interesting still, because once you accept that this air can be breathed by something, and this water can be lived in by something, the next question is not whether life can persist without the sun, but how it manages to build an entire food web there in the first place. That question takes us to the centre of the whole cave, because once you set sunlight aside, everything familiar about a food web seems to go slightly loose at the hinges. On the surface, we're used to thinking of life as a bright arrangement. Plants, algae and cyanobacteria gather light, turn carbon dioxide into organic matter, and from there the rest of the system more or less queues up for dinner. Remove the light, and the whole arrangement appears as though it ought to collapse. That is why Movile Cave matters so much. It shows that life can build an entire working system underground in complete darkness, without any meaningful input of organic matter from the surface, by using chemistry instead. UNESCO's description of the site is quite direct about this. The cave's biosynosis is sustained solely by organic matter and energy, produced in situ by chemosynthesis, in the absence of light and exogenous input. The 2021 review in Diversity makes the same point, describing Movile as the first terrestrial groundwater ecosystem discovered to depend entirely on chemosynthetic primary production. So when people say life there exists without sunlight, they do not mean that a few hardy creatures are surviving on leftovers in a gloomy corner. They mean that the base of the food web itself is being made in the dark. The practical difference between photosynthesis and chemosynthesis is easier to grasp than the long words suggest. Photosynthesis uses light as the energy source. Chemosynthesis uses the energy released by chemical reactions involving compounds such as hydrogen sulfide, methane, ammonium, and nitrite. In Movile Cave, those compounds are supplied by the deeper thermomineral waters feeding the system, and microorganisms are the ones doing the hard work. They oxidize reduced chemicals and use the energy gained to fix inorganic carbon into organic matter. If that sounds suspiciously efficient, it is because it is. The cave does not need a leaf, a blade of grass, or a shaft of sunlight to begin making food. It needs the right microbes in the right place with the right chemistry. The ISME journal study from 2009 provided molecular evidence that Movile is driven mainly by sulfur-based chemolithoautotrophy, while also showing that ammonia and nitrite oxidizing bacteria may be major primary producers as well. In other words, the cave does not run on one single clever trick. It runs on several linked chemical pathways, all of them exploiting compounds most surface animals would regard less as a meal and more as a warning label. That is where the microbial biofilm becomes so important. In Movile Cave, the thick floating pellicles and microbial mats are not decorative slime, though I realise that phrase may not be the marketing triumph the microbes were hoping for. They are the productive foundation of the ecosystem. UNESCO calls the microbial biofilm the key element of the site and the place of primary production by chemosynthesis, providing energy and organic matter, food and habitat for the invertebrate species. These pellicles form especially in the air bells, where the cave water meets limited oxygen above, and the chemistry becomes ideal for certain sulfur and methane-linked microorganisms. Researchers have described the water surface there as covered by thick mats or loose veils, sometimes up to a couple of centimetres thick, supported in part by methane bubbles. This means the base of the cave's economy is concentrated right at the interface between toxic water and poor air, which feels entirely in keeping with the cave's general habit of placing important things in the least welcoming location possible. Still, from the perspective of life, it makes perfect sense. Interfaces are often where the best opportunities live, because that is where chemical gradients are sharpest and energy can be harvested most effectively. If you look more closely at who is doing this work, the story becomes even more interesting. The 2009 ISME journal paper found sulfur oxidizers from both gamma and beta proteobacteria, and stable isotope probing showed that Theobacillus species were among the most active in assimilating carbon dioxide. The same study also detected Nitrosomonas and sequences related to nitrite oxidizers such as Nitrospira and Candidatus nitrotoga, which suggested that ammonia and nitrite oxidation may also be contributing substantially to primary production. So the cave is not supported by some vague cloud of bacteria doing mysterious bacterial things. It is supported by a set of identifiable metabolic specialists participating in sulfur and nitrogen cycling. More recent work has added further detail. A 2023 study in the ISME journal found that the surface water microbial community in some aqueous chambers is dominated by a cave-adapted species of Theovolum named Candidatus theovolum stegium, and concluded that it likely plays an important role in both sulfur and nitrogen cycles by switching between sulfide oxidation with oxygen and with nitrate as electron acceptors. That is a neat trick in any environment, and particularly useful in a cave where oxygen is scarce, sulfide is abundant, and flexibility is obviously an asset. Methane adds another important layer to life without sunlight, because not all of the cave's primary or near-primary production is built only around sulfur. The cave atmosphere and waters are enriched in methane, and both older and newer studies point to methane oxidation as an important process in the ecosystem. The 2009 ISME paper reported a significant number of methylotroph-related sequences, supporting the idea that cycling of one-carbon compounds matters in Movile Cave. Later work isolated a methane-oxidizing bacterium from the system, and broader metagenomic comparisons published in Frontiers in Ecology and Evolution. Note that Movile's methane-enriched atmosphere, fed by thermal waters, helps explain the relative abundance of methane-oxidizing bacteria in the microbial mats. That may sound a little technical, but the basic point is simple enough. Some microbes in the cave treat methane the way surface organisms might treat sugars or other readily useful compounds. They use it, transform it, and pass the products of that chemistry back into the wider food web. When you put sulfur oxidation, ammonia oxidation, nitrite oxidation, and methane-linked metabolisms together, the cave begins to look less like a miracle and more like a very unusual but coherent industrial district, with different specialist workers handling different parts of the same underground economy. What makes this especially striking is that carbon still has to come from somewhere. Whether life is powered by sunlight or by chemistry, cells must still build themselves out of carbon-containing molecules. In surface ecosystems, plants and algae fix carbon dioxide using light energy. In Movile Cave, chemolithoautotrophic microbes do a comparable job using chemical energy. The ISME study specifically used carbon-13 bicarbonate probing to show active carbon assimilation by sulfur oxidizers and to infer activity by ammonia and nitrite oxidizers as well. That is important because it moves the discussion from the cave contains odd microbes to the cave contains microbes measurably building biomass from inorganic carbon. Once those microbes produce organic matter, other organisms can feed on the biofilm, graze on associated microorganisms, or consume each other. This is how life without sunlight avoids becoming merely a slogan. It is not a mystical exemption from biology. Carbon is still fixed, energy is still harvested, biomass is still built, consumers still eat producers, predators still eat consumers. The difference is not that the usual ecological logic has been suspended. The difference is that the first step in the chain happens through chemistry rather than through light, and once you accept that shift, the rest of the food web becomes easier to understand. Strange, certainly, but not magical. The consumers in this system are not all aquatic either, which is another reason the cave feels so complete. UNESCO describes a surprisingly rich community of aquatic and terrestrial invertebrates, supported entirely by this in situ chemosynthetic production, and the 2021 review reports more than 50 invertebrate species in the cave and associated aquifer, including both aquatic and terrestrial forms, many of them endemic. In the microbial mats themselves, metazoans are dominated by nematodes, with copepods and ostracods also present in notable numbers. Beyond those come a wider cast of cave-adapted life, including snails, worms, isopods, water scorpions, spiders, pseudoscorpions, centipedes, millipedes, springtails, and beetles in the broader ecosystem descriptions. This matters because it shows that the cave has moved well past the stage of merely being microbiologically interesting. The microorganisms are the base, yes, but they support a community with multiple trophic levels and a range of feeding strategies. Some species graze directly on the biofilm, others feed on detritus derived from it, others are predators. That is the point where the idea of life without sunlight becomes properly impressive. not because one or two bacteria learned a chemical trick, but because enough organic production is generated in the dark to sustain a whole little society of animals. There is also a useful correction here to how we usually imagine darkness in ecology. We often treat darkness as simple absence, as though once the sun is removed, the story becomes one of deprivation and decline. But Movile Cave suggests that darkness can be more like a filter. It removes one set of possibilities and leaves room for another. Without sunlight, you do not get green plants, photosynthetic algae, or the familiar visual cues of surface productivity. What you do get, under the right chemical conditions, is a quieter form of productivity concentrated in films, veils, sediments, and interfaces. The thick microbial pellicles in the cave are not impressive in the same way a forest canopy is impressive. Nobody stands beneath them in wonder while birds sing overhead. They are not picturesque. They are, however, highly effective. UNESCO notes that the air bells where these pellicles form have been specially protected, because they are the very site of primary production by chemosynthesis. That is rather wonderful in its own understated way. In much of the surface world, primary production arrives as a meadow, a marsh, a reef, or a stand of trees. In Movile Cave, it arrives as a film on dark water and foul air, and it does the job just as seriously. From an evolutionary point of view, this sort of system is invaluable because it demonstrates that life can remain productive in the long term without any reliance on the sunlit surface. Movile Cave is commonly described as having been isolated from surface inputs for roughly 5.5 million years, and its obligate cave dwellers show the usual suite of subterranean adaptations: reduced or absent eyes, lack of pigment, and modified sensory structures. But the interesting part for this section is not just that the animals adapted to darkness. It is that the whole food web remained viable for immense spans of time while doing so. A cave can only become an isolated evolutionary workshop if there is enough dependable energy flowing through it to keep populations alive generation after generation. That is why the microbes matter so much. They are not an interesting footnote below the better-known cave animals. They are the reason those animals exist there at all. Without the ongoing chemosynthetic fixation of carbon and the recycling of sulfur, nitrogen, and one-carbon compounds, there would be no long-term isolation story to tell, only a sterile hole in limestone. Instead, Movile Cave gives us a hidden ecosystem that has been productive enough for speciation, specialization, and ecological layering to continue underground over geological time. It is no surprise, then, that astrobiologists and planetary scientists have taken an interest in places like this. Movile Cave is frequently discussed as an analogue for environments where life might exist without sunlight elsewhere, because it demonstrates that sunlight is not the only workable energy source for a biosphere. The cave is terrestrial, accessible, and comparatively small, but in principle it broadens the menu of habitability. If microorganisms can build a food web in the dark using reduced chemicals rising from rock and water, then worlds or subsurface environments without surface photosynthesis begin to look a little less impossible. That does not mean every dark place with a bad smell is secretly thriving, which is probably just as well. But it does mean that the boundary between livable and unlivable is not where our daylight habits once told us it was. UNESCO makes a similar point in more formal language by comparing Movile to deep-sea hydrothermal vent ecosystems, and noting that, at the time of its discovery, known chemosynthesis-based ecosystems were associated chiefly with ocean floor vents. Movile brought that logic onto land and into a cave. It took what seemed like a specialized marine exception and showed that the principle could operate in a subterranean limestone system near the Black Sea. That is the sort of discovery that quietly rearranges several assumptions at once. Even so, it would be misleading to make life without sunlight sound easy. Movile Cave is productive, but it is not lavish in the way a rainforest or estuary is lavish. Energy enters the system through narrow chemical routes, in a physically harsh setting, under conditions most organisms would not tolerate. The microbes that form the base of the food web are specialists, not generalists. The animals are specialists too. Everything about the ecosystem suggests constraint, efficiency, and long adaptation to a stable but difficult environment. That is partly why the cave feels so compelling. It is not a story of abundance in the usual sense. It is a story of precision. The right compounds must be present. The right microbes must be able to exploit them. The right interfaces between oxic and anoxic zones must exist. Consumers must be able to use the resulting biomass. Predators must survive on top of that. It is a narrow path, but over millions of years it has clearly been enough. There is something satisfying in that. Life does not always need broad sunny generosity. Sometimes it makes do with a thin chemical margin and builds patiently from there, which is a skill many of us might admire, while still preferring our own meals to arrive from less sulphurous supply chains. So when we say Movile Cave holds life without sunlight, what we really mean is that it holds a complete ecological argument against our own surface bias. The cave shows that light is not mandatory, that primary production can happen in darkness, that microbial films can stand in for meadows, that sulfur and methane can support a food web where chlorophyll never appears, and that a chemically powered ecosystem can persist long enough to generate its own distinctive animal community. It is one of the clearest reminders that life is less sentimental than we are. It does not insist on blue skies, green leaves, and a nice moderate breeze. Give it a usable gradient, a source of reduced compounds, time, and enough stability, and it will attempt something. In Movile Cave, it attempted a hidden world and succeeded, and once you know that, the creatures themselves become even more interesting, because they are not simply cave animals living in darkness. They are the residents of a place where darkness stopped being a lack and became the normal background to an entirely different kind of living. By the time most animals arrive in a story, we expect them to make some sort of entrance. A flash of feathers, a roar, a glint of eyes in torchlight, something to let us know the cast has assembled. Movile Cave does not care for that sort of theatre. Its creatures do not announce themselves. Many of them cannot see, several lack pigment, and almost all of them belong to a world where silence, darkness, chemical oddness, and long isolation have shaped body plans more effectively than any dramatic flourish ever could. A 2021 review counted 52 invertebrate species from the Movile Cave ecosystem, including 21 aquatic and 31 terrestrial species, with 37 endemics. Since then, the fauna has continued to be refined, including the description of a new ostracod species from the cave's sulfidic waters in 2023. That is a remarkable total for such a small and physically hostile place, but the number alone is not the most striking part. What matters more is that these are not random strays washed underground by bad luck. They are residents. Some lineages are ancient cave specialists, others appear to have colonized later, but together they form one of the richest known subterranean invertebrate communities sustained entirely by chemosynthetic production. If you picture them as pale, hesitant things barely clinging on in the dark, it helps to adjust that image slightly. Cave life often gets described as fragile because many species are highly specialized and vulnerable to disturbance, which is true enough from a conservation point of view, but that can make them sound feeble. They are not feeble, they are precise. UNESCO's site description notes that many of Movile's endemic terrestrial invertebrates show the classic features of obligate cave adaptation: loss of eyes, depigmentation, and elongated antennae and legs. That combination tells a very clear evolutionary story. If vision is no longer useful, the structure supporting it can be reduced. If colour no longer matters, pigment becomes a needless expense. If touch and chemical sensing become more important, limbs and antennae can lengthen and become more informative. It is not that the cave has taken things away and left the animals diminished. It has rearranged priorities. In a world with no daylight, no seasons worth noticing in the usual way, and very little room for sensory waste, the successful creature is the one built for contact, gradients, surfaces, vibrations, and chemistry, rather than for spectacle. The silence of the title is not only acoustic, it is evolutionary. These animals have been shaped by a world that does not reward display. The aquatic residents are perhaps the easiest way into this hidden caste, because they live directly on or in the sulfidic waters that make the cave so infamous. Among them are nematodes, rotifers, crustaceans, worms, leeches, snails, amphipods, isopods and ostracods, all participating at different levels in the food web built on microbial production. UNESCO species list includes the blind leech, Hemopus caeca, the snail Heliobia dobrogica, amphipods such as Pontonophagus racovitzi and Nephagus dankowi, isopods such as Acellus aquaticus infernus, and an ostracod that more recent work formally described as Pseudocandona movleiensis from the sulfidic lake room. When you lay those names out one after another, you begin to see the shape of the cave's aquatic community. It is not one marquee creature and a crowd of anonymous support staff. It is an assembled system of tiny grazers, detritivores, scavengers, and predators, some of them minute, some more conspicuous, all tied back to the microbial mats and films that produce the cave's organic matter. Life here is not decorative, it is integrated. Even the smallest crustacean belongs to an economy with rules, dependencies, and consequences. One of the most memorable animals in that watery caste is the cave's water scorpion, Nepa anophthalma. The word scorpion is admittedly unhelpful if one is trying to remain relaxed before sleep, but in this case we're not talking about a desert arachnid with a flair for melodrama. Water scorpions are aquatic true bugs, rather flat-bodied and rather patient, equipped for life in freshwater habitats and known for their predatory habits. What makes Nepa anophthalma so extraordinary is not simply that it lives in Movile Cave, but that the original 1994 description identified it as a blind cave-adapted species and the first aquatic stygobiotic heteropteran discovered. That is an impressive title, even if it does sound like the sort of thing one says to guarantee nobody sits next to you on a train. In practical terms, it means this insect is a proper subterranean specialist, not a surface species making the best of a bad relocation. It belongs to a lineage of surface water predators, yet here it is in low oxygen sulfidic darkness, hunting in one of the oddest aquatic environments known. It is exactly the sort of animal that makes Movile Cave feel less like a curiosity and more like a quiet insult to our assumptions about what insects ought to be willing to put up with. Then there is Hemopus caeca, the blind leech, which sounds like the sort of resident one prefers to encounter in literature rather than in person. But in ecological terms it makes perfect sense. A leech in Movile Cave is not there for atmosphere, although it does contribute generously to that. It is part of the aquatic predatory guild, living in water that is warm, sulfidic and poor in oxygen by surface standards. UNESCO lists it among the cave's endemic fauna, and broader food web descriptions place leeches among the predators feeding on organisms ultimately supported by the microbial base of the ecosystem. This is an important point because it reminds us that the cave's animals are not all feeding directly on slime, however vivid that image may be. Some are hunters. Once a system produces enough small grazers and scavengers, predation follows as naturally underground as it does in a meadow or pond. The cave's silence does not mean passivity. It simply means the chase is happening without birdsong, without leaves rustling, and without anyone seeing much of anything. The transactions of predator and prey continue all the same, just in a setting where the world has narrowed to touch, chemistry, and the nearby shape of survival. The cave's only known gastropod, Heliobia dobrogica, tells a slightly different story, and in some ways a more useful one. The snail is not only a resident of the cave, but the subject of a molecular clock study, suggesting it colonised the underground voids associated with the thermal sulphurous waters about 2.172 million years ago, significantly later than the earliest proposed isolation events for the ecosystem as a whole. UNESCO cites that result, and the 2008 molluscan study describes H. dobrojica as the only gastropod species living in Movile Cave. This matters because it prevents the fauna from sounding too neat. Not every creature in Movile is necessarily a survivor from the same ancient entry event. Different lineages may have arrived at different times, then become trapped, adapted, and transformed in place. The cave is a sealed world, but not one assembled in a single instant. It is more like a long-running subterranean household that admitted certain tenants at different moments, and then quietly changed them all according to its own rules. In the case of Heliobia dobrojica, that means a small snail becoming part of a dark, chemically unusual habitat where non-predatory animals feed on chemoautotroic microorganisms rather than on the plant detritus or algae we would expect in a more ordinary freshwater setting. Even a snail in Movile Cave has had to give up ordinary expectations. The terrestrial fauna is just as intriguing and perhaps even more varied. The 2021 review describes the land-based community as including isopods, spiders, pseudoscorpions, mites, centipedes, millipedes, springtails, diplurans, and beetles. UNESCO's species list includes endemic terrestrial crustaceans such as Trachelopus troglobius and Armadillidium tabacarui, arachnids such as Agracina christiani, Hania caeca, and several pseudoscorpions, along with cave springtails like Deuterophorura movili and Oncopodura viorelli. This is where the cave starts to feel almost mischievous. One can perhaps just about accept blind aquatic worms and crustaceans in a sulfidic cave if one is already in a generous mood. But then the terrestrial roster adds woodlice, spiders, diplurans, beetles, and centipedes, all using the same chemosynthetically fueled world as their stage. There is something deeply satisfying about that variety because it proves the cave is not merely a narrow chemical niche with a few specialist microbes and a lonely leech. It supports a whole invertebrate community on land as well as in water, and many of those terrestrial species bear the unmistakable marks of deep cave adaptation. They do not look unfinished, they look revised. Among the spiders, Agracina christiani has become one of the better-known names associated with the cave, partly because cave-adapted spiders are always memorable, and partly because Movile's spiders help demonstrate that darkness does not flatten the food web into harmlessness. The 2021 review notes that larger spider species such as Agracina christiani and Dysdera hungarica prey mainly on springtails and also on smaller isopods. That is a pleasingly practical detail. It gives the cave back some motion. You can picture the tiny ground-level world of pale springtails and woodlice moving through the damp darkness, and somewhere among them a spider built not for webs in sunlight, but for life in warm, air-poor chambers where prey is found by contact and chemical cues. UNESCO also lists Agracina christiani among the endemic terrestrial fauna and points to the typical troglomorphic traits seen in cave specialists. So this is not merely a spider that happens to be underground. It is a spider from a lineage that has been edited by the cave. The world above has no use for that design. The world below evidently does. If the spiders patrol with a certain quiet efficiency, the centipedes bring a more old-fashioned sense of menace, which is not at all a criticism. In 2020, researchers formally described Cryptops speleorex from Movile Cave, showing that what had long been thought to be the widespread European species C, anomalans, was in fact a distinct cave species. The paper describes C. speleorex as the largest invertebrate species in the cave and notes its troglomorphic traits, including a generally large body and elongated appendages and spiracles. It is difficult not to admire the name as well. Speleorex translates roughly to cave king, which is either taxonomic boldness or a very knowing wink from the authors. The centipede has been observed feeding on cave isopods, and is treated as a top terrestrial predator in descriptions of the food web. That makes it a useful emblem for the chapter, because it reminds us that silence underground does not mean gentleness. It means the hierarchy has been miniaturized and hidden, there is still a hunter at the top. It simply happens to be a pale centipede in a Romanian cave, rather than something with antlers or a more expensive documentary soundtrack. Some of the most revealing residents, though, are not the predators, but the small primary consumers and detritivores that form the living middle of the cave society. Isopods such as Trachylepus troglobius and Armadillidium tabacarui, springtails such as Deuterophora movile and Oncopodura viorelli, and various worms and crustaceans are the sort of animals that keep an ecosystem honest. It is easy to build a legend around the largest predator or the weirdest aquatic bug. It is harder, and more scientifically useful, to notice the quiet majority doing the steady work of grazing, feeding and being eaten. UNESCO species list and the 2021 review both show that Movile Cave's community is rich in exactly these sorts of creatures. They browse microbial production, process organic matter, move nutrients through the system, and provide prey for the higher levels above them. They are also the animals most likely to show the cave's design logic in its clearest form: reduced vision, little pigment, long appendages, sensitivity to moisture and chemical gradients, and a life spent close to surfaces in a world where the most important information is rarely at a distance. A cave ecosystem is often easiest to understand when you stop asking who the star is and instead watch who keeps the place running. In Movile, that answer is a great many small animals doing patient work in the dark. What is especially striking is how these creatures seem to embody different chapters of the cave's history at once. UNESCO's tentative World Heritage description suggests that terrestrial colonization may have begun with events linked to the Messinian crisis around 5.5 to 5.2 million years ago, while some aquatic colonization may have continued later through underground spring systems and coastal connections. The snail Heliobia dobrogica appears to represent one such later arrival, around 2.17 million years ago. That gives the cave fauna a kind of layered time depth. Some species may be ancient holdovers from very old isolating events. Others may have entered later and then undergone their own cavewood transformations. The result is not a single frozen relic community, but a dynamic long-term assemblage shaped by repeated opportunities for colonization, followed by harsh filtration and adaptation. The creatures evolved in silence, yes, but not all from the same moment of silence. Some have been listening to it for longer than others. That makes the fauna feel less like a museum display and more like a population history written in legs, mouth parts, antennae, and missing eyes. There is finally something quietly moving about how unshowy these animals are. Surface life often advertises itself. It sings, flashes, blooms, scents the air, and fills the daylight with signals. Movile's creatures have done almost the reverse. They have spent immense spans of time reducing what no longer helps, refining what does, and settling into a world with different priorities. Their environment does not reward colour, broad vision, or wasteful ornament. It rewards persistence, sensitivity, efficiency, and the ability to live close to a microbial economy most of us would rather discuss than encounter. And yet, from that unpromising arrangement has come a whole hidden fauna. Blind water scorpions, cave snails, leeches, amphipods, woodlice, spiders, springtails, pseudoscorpions, beetles, and a centipede grandly named Speleorex. The silence, in other words, has not emptied the cave, it has edited it. It has taken a piece of the surface world, or several pieces at different times, and rewritten them line by line into residents of a place where sunlight never arrives, and chemistry does the work of weather. Which is why the next step in the story is not simply to admire these creatures for being strange, but to look more closely at what millions of years of that kind of isolation actually do to a living system over time. What isolation did to Movile Cave was not simply to preserve it. It changed the terms of life there so thoroughly that the cave stopped being a refuge and became a sorting mechanism. Over immense spans of time, species that could not tolerate darkness, low oxygen, sulfide-rich water, and a food web built on chemosynthesis were removed from the equation. while the ones that could tolerate those conditions were pushed into a different kind of evolution altogether. UNESCO's description of the site links the underground colonization of the ecosystem to major geological events, especially the Messinian crisis around 5.5 to 5.2 million years ago, and notes that the composition of the invertebrate community still reflects that deep history. In that sense, isolation was not a passive backdrop. It was the main pressure shaping what kinds of bodies, behaviours, and relationships could persist underground. What changed was not just who lived there, but what counted as a useful trait in the first place. It is tempting to imagine the cave's fauna as one ancient group that disappeared below ground in a single dramatic moment, and then remained frozen there ever since. But the evidence suggests something more layered than that. UNESCO's site description notes that not all colonization happened at once. It points to the Messinian crisis as an early trigger for underground retreat, and also to the much later worm glaciation as another period that may have favoured colonization. The aquatic snail Heliobia dobrogica provides one of the clearest examples of this staggered history. Molecular clockwork estimated that this species invaded underground voids, associated with the thermal sulfurous water, about 2.172 plus or minus 0.171 million years ago, long after the earliest proposed isolation events for the system as a whole. That means Movile Cave is not simply a sealed time capsule filled with one generation of ancient exiles. It is more like a long-running subterranean experiment into which different lineages entered at different moments, only to be tested by the same dark, chemically difficult conditions. Isolation, then, did not just trap a community, it kept revising it. Once a lineage entered that underground system, the cave's environment did the rest with rather little sentiment. Sulfide-rich groundwater habitats are not just harsh in a general dramatic sense. They also create a peculiar combination of abundant chemosynthetically produced food and strong environmental filtering. A 2023 overview of groundwater invertebrates in extreme habitats notes that sulfidic habitats can offer enhanced resource availability, reduced exposure to predators, and a larger variety of ecological niches compared with more classical aquifers, while at the same time favouring only highly specialised species. The same review describes adaptation to hydrogen sulfide-rich settings as something that can promote speciation and biodiversity hotspots with high endemism. Movile fits that pattern almost too well. Despite its isolation from the surface, it has one of the most diverse subterranean invertebrate communities known, with 37 of 52 listed species in that review described as endemic to the cave. In other words, the cave is not species-rich in spite of its hostility. It is species-rich partly because the hostility acts as a filter, while the chemosynthetic food base keeps enough energy moving through the system to sustain niche differentiation and long-term persistence. This is where millions of years of separation start to show up in bodies. UNESCO notes that many of the endemic terrestrial invertebrates from Movile and the associated ecosystem display the classic traits of obligate cave dwellers: lack of eyes, depigmentation, and elongated antennae and legs. The Frontiers Review says much the same for the aquatic fauna, adding that despite differences in habitat, nutrient availability, chemistry, and ancestral variability, there is a parallel evolution of eye loss, depigmentation, and elongation of appendages among stygobionts in sulfidic groundwaters, including Movile. That phrase parallel evolution is important because it tells us these changes are not random oddities. Different lineages, arriving with different histories, keep ending up with similar solutions because the cave keeps asking similar questions. Can you gather information without sight? Can you navigate by touch, vibration, and chemical gradients? Can you economize on pigment in a world where color is useless? Can longer appendages help you sample the nearby world more effectively when distance vision has lost its point? Over long enough timescales, the answers start appearing again and again in leg length, antenna shape, eye reduction, and color loss. Isolation changed the animals by making the same features repeatedly worth keeping, and the same others repeatedly worth discarding. The easiest way to see that process in action is through specific species that were once mistaken for ordinary relatives. The cave's top terrestrial predator, the centipede Cryptops speleorex, was only formally recognised in 2020. Before that, the cave specimens had been treated as the widespread surface species Cryptops anomalans. Morphological and molecular analyses showed they were not the same thing at all. The new species is now described as the largest invertebrate in the cave and as a distinctly troglomorphic form with a generally larger body, elongated appendages and spiracles and other derived traits. That is exactly the kind of taxonomic revision one expects in a system shaped by long isolation. A lineage that once looked close enough to a surface cousin is revealed, under closer study, to have become something separate. The cave did not merely darken a surface centipede, it turned it into another species. That is a much stronger statement about what isolation does. It does not simply bend behaviour for a while. It can carry a lineage across the line where resemblance is no longer identity. Something similar appears in smaller animals too, and in ways that are easy to miss if you only look for dramatic predators. The 2023 description of the ostracod Pseudocandona movilensis presents Movile's sulfidic ecosystem as an evolutionary hotspot, and says the new species shows homoplastic traits found in unrelated stygobitic forms, including simplification of limb ketotaxy and a modified carapace shape, consistent with convergent or parallel evolution after colonization of the groundwater realm. That is a wonderfully precise example of isolation changing everything on a miniature scale. It means that even among tiny crustaceans, the cave environment has repeatedly favoured certain structural simplifications and body plans. When unrelated subterranean lineages start converging on the same sort of design, it suggests that the environment is not merely allowing survival, it is prescribing a limited menu of workable forms. The cave becomes a tutor with very strict marking criteria. Whether the student is a centipede several centimetres long or an ostracod measured in fractions of a millimetre, the lesson is much the same. Unnecessary traits are expensive and useful ones get refined. Isolation also changed physiology, and in Movile Cave that may be even more significant than body shape. The Frontiers Review notes that a characteristic feature of the aquatic invertebrates in Movile is the ability to endure high levels of hydrogen sulfide and low oxygen or hypoxia. That is not a minor adjustment. Hydrogen sulfide interferes with cellular respiration in many animals, and chronically low oxygen is the sort of condition that quickly narrows who can live where. Yet the cave's aquatic fauna persists in exactly those settings, in some cases not just in the cave itself but in the associated sulfidic aquifer around Mangalia as well. The same review points out that several of the cave's stygobites, including Nephagus dankawi, Eucyclops gretoricithecus, and a new ostracod from Pseudocandona, are also found in the wider sulfidic aquifer. That tells us something subtle but important. Isolation did not merely create a little island fauna with odd-looking bodies, it selected for physiological capacities that define an entire hidden groundwater province. In a sense, the organisms are not simply adapted to darkness, they are adapted to a chemical regime. The cave changed their relationship not only to light, but to oxygen, sulfide, and survival itself. Food relationships were altered just as deeply. On the surface, most ecosystems rely on photosynthesis, and that fact quietly shapes almost everything above it. In Movile Cave, the trophic web had to be rebuilt around microbial primary production fueled by sulfur, methane, and nitrogen chemistry. The Frontiers Review describes Movile's trophic web as remarkably complex, with chemoautotrophic microorganisms at the base and a rich meiofauna and predator guild above them. UNESCO similarly describes the entire biocenosis as sustained by chemolithotrophic bacteria that convert toxic hydrogen sulfide and methane into organic matter. Over millions of years, that has changed not just who eats what, But what sort of ecological opportunities exist at all? There is no plant layer, no seasonal fall of leaves, no sunlight-driven bloom and bust. Instead, there are microbial films, bacterial veils, chemically productive interfaces, and consumers specialise for exploiting them. Isolation therefore changed the cave's food web from the bottom up. It did not merely remove sunlight, it replaced the ordinary base of an ecosystem with another one altogether, and then let evolutionary time build upward from there. That different food base also changed the structure of competition and predation. In more typical caves, life often depends heavily on whatever organic matter trickles in from outside, which can make the entire ecosystem sparse and unstable. Movile had another option. Because chemosynthetic microorganisms continuously produced organic matter in situ, the cave could support a more intricate and abundant invertebrate community than many subterranean systems of comparable size. The 2023 overview attributes the relatively large diversity and complex trophic levels of sulfidic groundwater communities to this abundant and diverse chemosynthetic food source. In Movile, that means you do not just have one or two desperate scavengers nibbling at the same limited subsidy. You have grazers, detritivores, scavengers, active predators, and top predators operating in a chemically harsh but energetically functional world. Isolation changed everything here by turning what might have been a poor cave into a selective but productive one. It is an important difference. The cave is not rich because it is generous. It is rich because chemistry and time made a narrow but steady energy stream possible, and evolution packed that stream with specialists. The geographic meaning of home changed as well. UNESCO describes Movile Cave as the hotspot of a much broader ecosystem associated with the thermal sulphurous aquifer of South Dobruja, and suggests that the known aquifer covers an area of more than 50 square kilometres. Some cave species also occur in springs, wells, or other parts of the associated groundwater system. That means isolation did not create a single chamber full of exiles and then stop there. It created a hidden landscape. From our perspective above ground, it looks like separate localities. A cave here, a spring there, a well somewhere else, perhaps a discharge point in the sea. From the point of view of the organisms, those may be parts of one larger subterranean province linked by chemistry, water movement, and deep habitat continuity. Millions of years underground therefore change scale itself. The meaningful map is not the one we see on the surface. The meaningful map is the one drawn by the aquifer. For some species, Movile Cave is not the whole world but a neighbourhood in a world we only partly understand. Even time behaves differently in such a system. Surface ecosystems are often structured by seasons, weather swings, floods, droughts, and the sort of rapid environmental changes that reward flexibility. Movile Cave, by contrast, is notable for stable warm temperatures around 21 degrees Celsius, near saturated humidity, and persistent chemical conditions tied to the aquifer and cave atmosphere. Stability of that kind changes the tempo of selection. Instead of repeatedly rewarding broad tolerance to shifting surface conditions, it can favour long, steady refinement to a narrow and dependable set of subterranean ones. That does not mean evolution slows down in any simplistic sense. It means the direction of adaptation can become more consistent. In a system where darkness is constant, food comes from microbes, and sulfide and hypoxia remain familiar rather than exceptional, there is little advantage in keeping capacities meant for sunlit surface life. The result over very long periods is the sort of deep specialisation that makes cave animals seem almost inevitable once you know the rules they have been living under. Isolation changed everything partly by removing noise. It allowed the same conditions to keep teaching the same lessons for vast spans of time. There is a quiet irony in the fact that this same long isolation can make the fauna seem both ancient and surprisingly dynamic. Ancient, because many lineages show deep cave adaptation and a history linked to old geological events. Dynamic, because the species list keeps changing as researchers study the system more carefully. The Frontiers overview notes that by 2022, the addition of newly reported earthworms had brought the total number of species hosted in Movile to 54, and the cave has continued to yield newly described taxa such as Pseudocandona movilensis and Cryptops speleorex. That is a useful reminder that isolation changed not only the cave's biology, but our scientific understanding of it. Every newly described species is evidence that the hidden world is still not fully inventoried, even decades after its discovery. The cave has had millions of years to produce distinction, and we have had only a short time to catch up. In that mismatch there is something almost endearing. The organisms have been busy for geological ages. We as usual arrived late and brought notebooks. Perhaps the deepest change of all is that isolation seems to have turned ordinary evolutionary drift into a form of commitment. Above ground, many species can move, mix or retreat when conditions shift. In Movile Cave, options are fewer, the filters are stricter, and the same chemical and sensory world keeps pressing on generation after generation. Over that kind of timescale, traits do not merely fluctuate, they settle. Eyes vanish because there is no reason to keep building them. Pigment fades because there is no audience for colour. Sensory appendages lengthen because surfaces, vibrations and chemical traces matter more than anything far away. Tolerance to sulfide and hypoxia becomes part of the basic bargain of existence. Food webs reorganize around bacterial production rather than sunlight. Entire lineages diverge far enough from surface relatives to be recognized as distinct species. That is what millions of years of isolation changed. Not one thing, but the entire logic by which life in that place makes sense. And once you start seeing the cave that way, as a long and exacting evolutionary filter, the next piece to look at is the chemistry that never stopped applying that pressure in the first place. Because the creatures of Movile were shaped by time, yes, but time in this cave always arrived carrying sulfur, methane, and a very particular set of rules. If isolation was the long pressure that reshaped life in Movile Cave, chemistry was the hand applying that pressure every single day. This is really the part of the story where the cave stops sounding merely unusual and starts sounding like an ecosystem built according to a different set of engineering plans. On the surface, we are used to food webs beginning with light and water, and a patient green organism doing the first useful bit of work. In Movile Cave, that opening move comes instead from reduced chemicals rising with the groundwater. UNESCO describes the flooded lower level as rich in hydrogen sulfide, methane and ammonium, with dissolved oxygen measurable only in the upper few centimetres before conditions turn anoxic. The 2022 metagenomic study of Movile describes the cave as a closed chemoautotrophic system, driven by in-house sulfur and methane oxidation and carbon dioxide fixation, while the 2009 ISME journal paper concluded that the ecosystem is driven mainly by sulfur oxidation, and that ammonia and nitrite oxidizing bacteria may also be major primary producers. That is a very different menu from the one most ecosystems order from, but it works. The easiest way to make sense of that chemistry is to picture the cave not as one uniform underground room, but as a series of narrow opportunities where certain compounds meet certain other compounds under just the right conditions. Sulfidic groundwater rises from the deeper aquifer and flows constantly through the lower passages. Oxygen is scarce overall, and in the water column it penetrates only a tiny distance below the surface. The 2023 Theovulum paper reports that oxygen penetrates only the upper 0.8 millimeters of the water column, before the water becomes anoxic. That detail is almost comically severe. It means the most important chemistry in the cave is happening in a very thin boundary layer, at the exact place where the little oxygen available can still encounter the hydrogen sulfide and other reduced compounds supplied by the water below. Those interfaces are where the cave becomes productive. They are in effect the substitute for a sunlit meadow, tiny in thickness admittedly, and rather worse in smell, but functionally just as important. Hydrogen sulfide is probably the chemical at the centre of the whole arrangement. It arrives with the groundwater, It gives the cave its unmistakable rotten egg smell, and it provides a major energy source for sulfur-oxidizing microorganisms. The 2009 ILME study found strong molecular evidence that Movile Cave is driven mainly through sulfur oxidation by sulfur-oxidizing bacteria. The 2023 Theovulum study adds another layer by showing that the surface water microbial community in parts of the cave is dominated by a cave-adapted species named Candidatus, Theovulum stegium, a large sulfur bacterium that stores elemental sulfur inclusions inside its cells and appears to play an important role in sulfur cycling. These bacteria are not merely present, they are doing the first serious work of the ecosystem, stripping energy from reduced sulfur compounds and using it to support biomass production in darkness. In ordinary surface terms, hydrogen sulfide would register mostly as a nuisance or a hazard. In Movile Cave it is also lunch, or more accurately the thing from which lunch begins. That sulfur chemistry is not as simple as just turning sulfide neatly into sulfate and calling it a day. The 2023 study on cave Theovulum found that the cells carry sulfur inclusions, and that under mobile conditions, where hydrogen sulfide is supplied continuously and oxygen is scarce, complete depletion of those sulfur stores is unlikely. The paper identified the gene for sulfide quinone oxidoreductase, which converts sulfide to elemental sulfur, and noted that the known gene sets for fully oxidizing that sulfur onward to sulfate were not found in the same straightforward way. In plainer language, the cave's chemistry seems to favour an intermediate heavy sulfur economy rather than a tidy one-step conversion. Sulfur can accumulate inside cells, be stored, be reused, and be cycled through multiple states depending on local oxygen conditions. That makes sense in a cave where oxic and anoxic conditions sit almost on top of one another. The chemistry is not broad and airy, it is cramped, layered, and opportunistic. Reactions happen where they can, with whatever electron acceptor is available. And oxygen, such as it is only one part of that story. The same Theovulum study concluded that cave Theovulum can switch between aerobic and anaerobic sulfide oxidation, using oxygen when it is available and nitrate when it is not, likely through dissimilatory nitrate reduction to ammonia. That matters because it means the cave's sulfur cycle is tied directly into its nitrogen cycle. The bacteria are not just sulfur specialists in a narrow sense, they are chemical pragmatists. In a place where oxygen is scarce, being able to use nitrate as an alternative electron acceptor is an excellent career move. The authors concluded that Theovulum is likely important to both sulfur and nitrogen cycles in sulfidic caves. This is one of those details that turns the cave from a strange anecdote into a serious biogeochemical system. The microbes are not simply surviving around bad water, they are linking sulfur and nitrogen transformations in ways that stabilize energy flow and nutrient cycling through the whole ecosystem. Nitrogen chemistry, in fact, has been part of the Movile story for quite some time. The 2009 ISME journal paper did not stop at sulfur oxidizers. It also found evidence that ammonia and nitrite oxidizing bacteria may be major primary producers in the cave. That is useful correction to the simplified version of the ecosystem, which often gets told as though sulfur alone does all the heavy lifting, while everything else stands nearby nodding politely. In reality, nitrifying bacteria appear to contribute substantially to primary production as well. Ammonium from the groundwater can be oxidized, nitrite can be further oxidized, and the energy released can be used to fix inorganic carbon into biomass. So the cave's food base is not a single pathway enterprise. It is more like a tightly organized chemical consortium, with sulfur, nitrogen and methane all contributing to the bigger picture. The ecosystem works because several metabolisms overlap and reinforce one another, not because one lucky microbe found one convenient loophole. Methane is the other major player that gives Movile Cave its particular personality. UNESCO notes that the lower waters are rich in methane, and that the air bells contain air unusually rich in both carbon dioxide and methane. The 2009 ISME study recovered many sequences associated with known methylotrophs, supporting the view that cycling of one carbon compounds is an important process in the cave. The 2022 metagenomic paper likewise describes Movile as being driven by sulfur and methane oxidation. In practical terms, that means some microorganisms are exploiting methane as an energy and carbon source, converting part of that chemically reduced carbon into biomass or into intermediates that other organisms can use. This is another reason Movile resembles a deep-sea chemosynthetic system more than a typical cave. Methane, like hydrogen sulfide, arrives as part of the deep geochemical setting and becomes a usable input for life. The cave is therefore fed not by sunlight from above but by reductants from below. It is an upside-down kind of economy. Instead of energy raining down from the sky, it seeps upward through the rock. Once those chemical inputs are available, the next crucial step is carbon fixation. An ecosystem cannot run on electron transfers alone. Organisms still need carbon to build cells, tissues, and eventually centipedes with very strong opinions about being left alone. The 2022 metagenomic study describes carbon dioxide fixation as one of the primary production processes in the cave, and the 2009 ISME study provided direct molecular evidence for chemolithoautotrophy in Movile. In other words, microorganisms are using the energy gained from oxidizing sulfur compounds, ammonia, nitrite, and methane to fix inorganic carbon into organic matter. This is the exact point where strange chemistry becomes food. It is also the point where the cave stops being just a geochemical curiosity and becomes a functioning ecosystem. The difference between a sulfur-rich hole in the ground and a self-sustaining biosphere is precisely that step of taking inorganic inputs and turning them into living material. In Movile Cave, microbes do that first step so effectively that the rest of the food web can exist on top of it. The physical place where all this productivity becomes visible is the water surface in the lower cave and especially the air bells. UNESCO describes the air bells as confined pockets with reduced oxygen where the water surface can be covered by a microbial pellicle up to 2 centimeters thick, kept afloat by methane bubbles. The 2022 metagenomic study describes these water surfaces and adjacent walls as active redox interfaces colonized by floating microbial mats and biofilms. The 2023 Theovulum paper observed a loose floating veil at and directly below the water surface in the lower level and found it dominated by Theovulum. These descriptions are important because they let you picture the chemistry instead of leaving it as an invisible abstraction. The cave is not merely full of dissolved compounds, it has actual living structures at the surface, floating veils, thick films, mats, and biofilms where chemistry is being harvested in real time. If surface ecosystems advertise themselves with leaves, trunks, and grass, Movile advertises itself with veils of bacteria on dark water. Less picturesque, certainly, but very efficient. Those biofilms are not just food, they're also habitat. UNESCO notes that the pellicle consists of bacteria, archaea, and fungi, and serves as both habitat and food for various protozoans and metazoans. It even gives a rough breakdown of the metazoans living in the microbial mat, with nematodes dominating strongly and smaller shares made up by copepods, ostracods, and other invertebrates. That detail matters because it shows how directly the strange chemistry shapes the visible community. The animals are not feeding on plants that happen to have grown in an odd place. They are feeding on a microbial interface built by sulfur, methane, nitrogen transformations, and carbon fixation. The base of the cave's food web is therefore not just chemically unusual, it is physically concentrated and ecologically crowded. Whole communities gather at the exact places where redox gradients are sharp enough to support productivity. The cave's chemistry is not distributed gently and evenly. It creates hotspots, and life crowds around them. It also changes the cave itself. The same chemistry that feeds the microbes is involved in ongoing speleogenesis, which is a suitably dignified geological word for cave making. The 2022 metagenomic paper describes two main processes shaping Movile: sulfuric acid corrosion in the partially submerged lower level and condensation corrosion in the upper level. UNESCO similarly notes that the slightly warmer cave atmosphere leads to condensation on the walls and ceiling, where carbonic acid forms and accelerates dissolution of the limestone surface. In the lower cave, hydrogen sulfide-rich waters contribute to sulfuric acid processes, so the ecosystem's chemistry does not merely happen inside a pre-existing stage set, it helps reshape the stage. That is one of the most elegant parts of the whole system. The compounds that feed the microbes also contribute to carving and altering the cave environment itself. Life and geology are not acting in sequence, one after the other. They are entangled in the same chemical setting, each responding to and modifying the other. Another useful thing to notice is how narrow the productive zone really is. Oxygen reaches only the uppermost fraction of the water column, while hydrogen sulfide is available continuously from below. That creates a compressed redox gradient where very specific metabolisms can thrive. The cave is therefore not productive in the broad, generous way a lake or forest is productive. It is productive at interfaces. A few millimeters can separate aerobic from anoxic conditions. A slight shift in oxygen availability can alter which sulfur reactions dominate. The difference between the lake room and the air bells can change whether thick pellicles form at all. This fine-scale structure is part of why the chemistry feels so strange and so important. Everything depends on gradients. The cave is a world built out of boundaries: oxic against anoxic, sulfide-rich water against poor air, microbial veil against open surface, cave wall against condensing atmosphere. It is in those tight margins that the ecosystem earns its living. From a broader scientific point of view, Movile Cave matters because it shows that chemistry alone can sustain a complex terrestrial ecosystem over long periods. UNESCO explicitly describes it as the first discovered terrestrial self-sustained ecosystem dependent on chemoautotrophically fixed carbon, and notes that when it was found, the only known chemosynthesis-based ecosystems were those associated with deep ocean hydrothermal vents. That comparison is very helpful. It reminds us that Movile is not merely a strange cave with unusual water quality. It is proof that the logic of chemosynthetic life can operate underground on land in a sealed limestone system, provided the right geochemical inputs are available. Sulfur, methane, ammonium, nitrate, carbon dioxide, low oxygen, and stable thermal groundwater may not sound like the ingredients of anything cheerful, but they are enough to feed an ecosystem if the microbes know what to do with them. In Movile Cave, clearly they do. There's also something quietly amusing about how little the chemistry cares whether we find it appealing. On the surface, we tend to associate productivity with freshness. Healthy air, clean water, sunlight, green growth. Movile offers the opposite aesthetic and yet reaches the same ecological destination. It runs on rotten egg gas, methane-rich air pockets, ammonium-bearing waters, and barely any oxygen where it matters most. Its most important producers gather in floating veils and thick microbial films rather than in fields, leaves, or forests. And still, through those reactions, biomass accumulates, consumers feed, predators hunt, and an entire hidden community keeps going. That is perhaps the most useful thing this chapter's chemistry teaches. Life is not loyal to our preferences. It will use whatever gradients, molecules, and energy sources are available if they can be turned into workable metabolism. The cave's chemistry is strange only relative to our habits. To the organisms in Movile, it is the ordinary economy of home. So by this point in the descent, the cave has revealed the real engine under the floorboards. Hydrogen sulfide feeds sulfur oxidizers. Methane supports methylotrophs. Ammonium and nitrite feed nitrifying microbes. Carbon dioxide is fixed into biomass. Oxygen, when present at all, is squeezed into paper-thin zones at the water surface, and nitrate can take over where oxygen fails. Methane bubbles help keep microbial pellicles afloat. Acid-forming reactions continue to alter the cave walls. Every important part of the system is tied back to chemistry that most surface ecosystems scarcely notice. Which is why the next part of the story is less about theory and more about encounter, because once you understand what is feeding this ecosystem, the natural question is what it looked like when scientists finally entered that air, saw those floating veils, sampled that water, and realised they were not looking at some dead chemical oddity at all, but at a living world that had been working perfectly well without us. When scientists finally went inside Movile Cave, what they found was not the ordinary reward at the end of a difficult underground approach. It was not a pretty chamber, not a dry geological curiosity, and not simply a cave with a few pale insects and some stale air. Movile had been discovered in 1986, after being sealed from surface inputs for roughly 5.5 million years, and the first serious investigations quickly showed that it opened into something far stranger. A chemically extreme underground system, fed by sulfidic thermal groundwater and supporting a self-sustaining ecosystem in complete darkness. Later reviews would describe it as the first terrestrial ecosystem discovered to be sustained entirely by autotrophically fixed carbon. But the important thing at the beginning is that the researchers did not go in already looking at a familiar kind of cave. They went in and found a place that forced them to change what they thought a cave ecosystem could be. The physical route into that hidden world already told part of the story. Movile is reached by an artificial vertical shaft about 20 to 21 metres deep, leading into narrow dry passages above, and then into lower passages that are partially flooded and include the lake room and the air bells. UNESCO's site description notes the two-level structure clearly, an upper dry level and a lower flooded one, with the lower level accessible from the lake room and the ceiling rising in places to form isolated air pockets known as air bells. That layout helps explain why the early visits mattered so much. Researchers were not simply walking through one connected cavern. They were descending into a layered environment where each step downward took them farther from ordinary cave conditions and closer to the chemical heart of the system. Even before any complex ecological theory entered the picture, the cave structure itself was telling them that this place had compartments, gradients, and hidden zones that surface intuition was not going to explain very well. Then came the atmosphere, which was the sort of introduction one tends not to forget. Movile Cave is warm, with air temperatures around 21 degrees Celsius, near 100% humidity, little air circulation, and a strong sulfur smell that intensifies toward the deeper parts of the cave. In the upper passages the air is already unusual, but the deeper air bells are far more extreme, with oxygen dropping to around 7 to 10%, and methane and carbon dioxide becoming enriched. UNESCO describes the air bells as poor in oxygen and unusually rich in carbon dioxide and methane, while other summaries of cave conditions note hydrogen sulfide, ammonia and carbon dioxide in the air as well. So when scientists went inside, they did not first encounter a tidy specimen cabinet of strange animals. They encountered air that immediately announced this was a hostile environment by human standards. It is difficult to overstate how much that changes perception. Once a place makes breathing feel conditional, every other observation starts to look less like a curiosity and more like a challenge to basic expectations. The water was no more reassuring. The lower flooded passages contain thermal water rich in hydrogen sulfide, methane and ammonium, and the oxygenated zone at the surface is astonishingly thin. UNESCO notes that dissolved oxygen is measurable only in the first 5 centimetres below the surface, deeper than which the water is anoxic. More detailed later work found oxygen penetrating only the upper fraction of a millimetre in some places. Early investigators also described substantial microbial biofilms covering water surfaces within the air pockets. This means that what scientists found was not just bad air over odd water, but a highly stratified chemical system in which life had to make use of very tight redox boundaries. The water was warm, sulfide-rich, and largely devoid of oxygen below its uppermost layer, which is precisely the sort of setting most people would assume should be biologically poor. Instead, it turned out to be one of the most important productive surfaces in the whole cave. That reversal is part of what made the discovery so powerful. Everything about the physical setting seemed to say this should not work, and yet the evidence kept pointing the other way. One of the first truly startling sights was the microbial pellicle on the water surface in the air bells. UNESCO describes the surface of the water in the air bells as covered by a microbial pellicle up to 2 centimeters thick, kept afloat by methane bubbles, while the 1994 Microbiological characterization reported substantial biofilms on the water surfaces within the air pockets. These were not a bit of incidental slime on a neglected pool wall. They were extensive living films formed exactly where the cave's strange chemistry created the right interface between reduced compounds rising from the water and the limited oxidants available near the surface. At the time, that visual alone must have made it clear that the cave was not merely geochemically interesting. It was biologically active in a very direct way. The water surface was not empty, it was occupied. It was, in effect, growing the base of a food web in darkness. Most ecosystems advertise productivity with leaves, grass, or algae bloom. Movile was advertising it with thick microbial films floating in foul air over a noxic sulfidic water. There is no polite way to say it looked less like a garden than like a biochemical negotiation gone surprisingly well. And then there were the animals. Early studies reported that the air bells contained an abundant and diverse community of terrestrial and aquatic animal species, and UNESCO now describes the cave biosynosis as including both terrestrial and aquatic invertebrates, many of them endemic. The cave's species list has grown over time as work continued, but even the early picture was enough to show that this was not a system made only of bacteria. The microbial mats and biofilms were supporting a larger community, including nematodes, crustaceans, worms, snails, and predators. UNESCO notes that nearly 95% of the metazoans living in the microbial mat are nematodes, with copepods and ostracods also present, and that the wider fauna spans both land and water in the cave. That would have been one of the most decisive moments in understanding what Movile really was. If the cave had held only sulfur bacteria, it would still have been fascinating. But a productive microbial base plus a diverse animal community meant scientists were looking at a genuine ecosystem, not a microbiological footnote. The cave was not simply alive, it was organised. Just as important as what was present was what seemed absent. The cave community did not appear to be receiving meaningful organic carbon input from the surface. The 1994 Microbiological characterization used dehydrogenase activity, fecal streptococcus counts, and stable carbon isotope ratios to argue that the community was biologically isolated and received little, if any, organic carbon from above. That is one of the pivotal findings in the whole story, because it shifted the interpretation from unusual cave with odd conditions to a system that was effectively feeding itself underground. Later reviews echoed the same point, describing Movile as isolated from the surface and sustained by in situ chemoautotrophic primary production. This is where the intellectual shock of the discovery really settled in. It was one thing to find life in a poisonous cave. It was another to realise that the life there was not surviving on crumbs dropped by the surface world. The cave was running its own economy. It had its own producers, its own consumers, its own chemical energy inputs, and its own internal nutrient cycling. That is the point where discovery turns into reclassification. Scientists had not found an odd cave community. They had found a different model of how an ecosystem could work on land. The microbiology only deepened that impression. Early investigators isolated several sulfide-oxidizing chemoautotrophic bacteria from the cave waters, and the 1994 study specifically reported a putative Theosphaera strain with clear evidence of high rubisco activity, which is exactly the sort of enzymatic clue you hope to find if you suspect carbon fixation is happening in the dark. Later work expanded that picture dramatically. The 2009 ISME journal study provided evidence that the cave is driven mainly by sulfur-based chemolithoautotrophy, while also indicating important roles for ammonia and nitrite oxidizing bacteria. Later studies added methane oxidation and more detailed sulfur and nitrogen cycling, including dominance of thiovulum in some surface water communities. But even without all the later genomic refinement, the first message was already plain. Scientists had found microorganisms using chemical energy from sulfide-rich water to produce biomass in a lightless cave. Once that was established, the rest of the food web above them became interpretable. The biofilms were not a side effect, they were the engine room. There was another thing researchers found, though it is easier to phrase in hindsight than it would have been underground at the time. They found a system that looked, in broad, functional terms, more like a deep-sea vent ecosystem than like a typical terrestrial cave. UNESCO explicitly notes that when Movile was discovered, the only known chemosynthesis-based ecosystems were those associated with hydrothermal vents on the ocean floor. Movile brought that logic into a terrestrial groundwater setting. That comparison matters because it shows how radical the discovery was scientifically. Caves were known to support specialized life, of course, but usually through organic matter arriving from the surface in one form or another. Movile forced a different conclusion. Here was a cave in the southeastern Romania, where chemical energy from below, not sunlight from above, sustained a complex food web. Scientists did not just find a remarkable cave, they found a terrestrial exception big enough to redraw a category. In research terms, those are the finds people dream about and then spend the next decades carefully trying not to oversimplify. What they also found, inevitably, was that the cave resisted ordinary exploration. The dangerous atmosphere, the flooded lower passages, the confined air bells, and the fragility of the ecosystem all made it clear that this was not a place for casual visitation. Modern descriptions still emphasize that few people have explored the cave since its discovery because of the high concentrations of toxic gases, low oxygen, near total humidity, and almost non-existent air circulation. UNESCO's current description reflects the same essential reality through the cave's chemistry and the highly protected status of the site as the only accessible gateway to a unique, isolated ecosystem. That practical difficulty shaped the science itself. Movile had to be studied cautiously, episodically, and with the understanding that the presence of researchers could itself alter the environment. There is something almost fitting in that. A cave that remained hidden for millions of years did not become suddenly obliging just because we found it. It had answers, certainly, but only for people willing to go carefully and breathe with considerable respect. Perhaps the most lasting thing scientists found when they finally went inside was not any single species, gas reading or microbial mat, but a new sense of what counts as possible. They found warm air poor in oxygen, sulfur-rich water, anoxic depths, floating biofilms, abundant invertebrate life, and isotopic and microbiological evidence showing that the whole system was largely independent of the surface. They found that the cave's animals were not accidental visitors, but adapted residents, and that the microorganisms were not merely surviving, but producing the organic matter that supported the rest of the community. In one underground system, they encountered discovery in the old-fashioned sense of the word, something that was truly there before anyone knew how to think about it properly. And because of that, the next question almost asks itself. Once scientists understood what the cave was, and once the first astonishment settled into careful study, attention naturally shifted from what they had found to how such a place could keep functioning at all. Because one thing is to discover a hidden ecosystem, and another is to understand how life in such a place manages the daily business of staying alive in a world that still looks, to us, as though it ought to be dead. The easiest mistake to make with Movile Cave is to imagine survival there as a heroic exception, as though every organism is clinging on by its fingertips in a place that remains fundamentally hostile to life. That is how the cave looks to us, and not without reason. The water is rich in hydrogen sulfide, the oxygen is low, the carbon dioxide is high, the lower layers of water turn anoxic almost immediately, and sunlight does not enter the system at all. Yet one of the clearest lessons from the cave is that survival in such a place does not depend on stubbornness alone. It depends on a whole set of biological arrangements that make the cave's conditions workable, even productive, for the organisms that belong there. Reviews of the ecosystem emphasise that Movile supports one of the most diversified subterranean invertebrate communities known, with a remarkably complex trophic web built on chemoautotrophic microorganisms in sulfide-rich water and sediments. In other words, the world only seems dead if you apply surface standards too rigidly. That point matters because dead places, in the ecological sense, are places where energy cannot move into living systems in a dependable way. Movile Cave does not have that problem. It has a very unusual energy source, but it has one. Sulfur oxidizers, methane oxidizers, and nitrifying microbes turn reduced chemicals from the deep aquifer into biomass, and that biomass supports the rest of the food web. The 2009 ISME journal study described the system as being driven mainly by sulfur oxidation, while also showing that ammonia and nitrite oxidizing bacteria may be major primary producers. Later work on cave theovulum showed that one major sulfur bacterium in the cave can switch between aerobic and anaerobic sulfide oxidation, using oxygen when available and nitrate when it is not. That flexibility is not a decorative biochemical extra. It is one of the reasons the cave can keep running under conditions that would shut down more ordinary systems. Survival there begins with microbes that do not wait for ideal circumstances. They use the chemistry they are given. Once that microbial base is in place, the rest of the system stops looking like a collection of accidental survivors and starts looking like a community built for narrow margins. The Frontiers Review on Extreme Groundwater Habitats points out that sulfide-rich groundwater can offer enhanced resource availability, reduced exposure to predators, and a wider range of ecological niches than classical aquifers, even while remaining challenging for most organisms. That combination is important. Movile Cave is difficult, but it is not empty, and it is not resource-free. The microbial productivity in the cave means there is food, but the chemistry ensures that only certain kinds of consumers can exploit it. That is why the cave ends up with both high endemism and surprising trophic complexity. Survival in a world that should be dead works because the world is not simply harsh. It is selective. It excludes many organisms while strongly favouring those able to exploit microbial production under low oxygen and high sulfide. For the aquatic invertebrates, the main daily problem is chemical. The Frontiers Review states plainly that a characteristic feature of the aquatic invertebrates living in Movile Cave is their ability to endure high levels of hydrogen sulfide and low concentrations of oxygen, or hypoxia. That ability should not be treated lightly. Hydrogen sulfide is a respiratory toxicant at high concentrations, and low oxygen narrows the margin for life even further. The same review notes that sulfide can exacerbate the consequences of hypoxia and anoxia, making the cave's environment a multi-layered stress rather than a single inconvenience. Surviving there therefore means dealing with two link problems at once: not enough oxygen, and too much of a compound that interferes with the ability to use oxygen efficiently. It is not the kind of environment where a generic freshwater body plan can simply muddle through. It demands specific ways of keeping sulfide under control while enduring chronic oxygen limitation. Researchers studying sulfidic groundwater systems outline several broad ways in which adapted invertebrates can manage that challenge. The Frontiers Review summarises 4 major processes: reducing how much hydrogen sulfide enters the body through behavioural or structural strategies, limiting the harmful effects once it gets in, regulating internal sulfide levels through detoxification or sequestration, and in some cases relying on symbiosis with sulfur-oxidizing bacteria. Not every species uses every strategy, and there is still much we do not know about the exact physiology of Movile's fauna, but the framework is useful because it shows survival there is not one single trick. It is a set of solutions layered together. Some organisms may keep close to microhabitats where gradients are favourable. Some may tolerate sulfide biochemically better than surface relatives. Some may carry microbial partners that help manage the chemical environment on their bodies. The cave is therefore not occupied by invertebrates that somehow ignore the chemistry. It is occupied by invertebrates that negotiate with it constantly. Behaviour appears to matter as much as physiology. In oxygen-poor sulfidic systems, where the best conditions often occur at thin redox interfaces, simply being in the right place can save energy and improve survival. The Frontiers Review discusses related sulfidic groundwater crustaceans that maintain themselves at density layers where bacteria proliferate, allowing them to take advantage of oxygenated microzones while avoiding deeper anoxic stress. Movile's own ecology points in the same direction. The most productive surfaces in the cave are microbial films and veils at the water interface, exactly where oxidants and reduced compounds meet. It makes sense that many of the cave's consumers are tied closely to those surfaces rather than roaming widely through the water column. In a place where oxygen can vanish within millimeters below the surface, staying near the right boundary is not merely a preference. It is a survival strategy. The cave rewards organisms that can read gradients correctly and remain in the narrow zone where food is available and conditions are barely acceptable. That same logic helps explain why the cave's fauna often looks stripped down and elongated at the same time. Parallel evolution of eye loss, depigmentation, and elongated appendages has been documented among stygobionts in sulfidic and non-sulfidic subterranean waters, including species from Movile and the surrounding aquifer. The loss of eyes and pigment is often described as if it were simply the subtraction of unnecessary features, and in one sense it is. But the elongation of appendages is the more revealing detail because it points to how the animals gather information instead. In darkness, with visibility irrelevant, and in chemically layered environments where nearby surfaces matter more than distant scenery, long antennae, limbs, or other sensory structures become much more useful. Survival in Movile Cave is therefore not only about tolerating poison and hypoxia, it is also about sensing a world made of contact, gradients, and immediate surroundings rather than sightlines and colour. Microbial partners may be part of the picture too, and that possibility makes the cave feel even less like a set of isolated organisms and more like a network of negotiated arrangements. A 2013 study found that 6 of 7 nifigid amphipod species recorded in the Mangalia region, including 2 from Movile Cave, carried potential Theothrix ectosymbionts. The Frontiers Review goes on to note more recent molecular evidence for Theothrix associations on microcrustaceans such as ostracods and cyclopoids in the same sulfidic groundwater habitat. These symbioses are important because they may help animals live in hydrogen sulfide-rich environments by placing sulfur-oxidizing bacteria directly on their exoskeletons. The exact functional benefit can vary and is not fully mapped for every host species, but the larger point is clear enough. In Movile and its surrounding aquifer, survival may not always be an individual achievement. Sometimes it may be a collaboration between animal and bacterium, with each using the other's position in the cave's chemistry to stay alive. Even the cave's protists tell the same story in miniature. A 2019 study of microbial eukaryotes in Movile Cave found a wide diversity of protists, with ciliates especially prominent, and concluded that, consistent with local low oxygen conditions, many of these protists are likely anaerobic or microaerophilic. That is a useful reminder that survival in Movile is not just a question for the more charismatic residents, like water scorpions, snails, or cave centipedes. It applies all the way down the food web. The microbial mats are not inhabited only by bacteria, they also support eukaryotic microorganisms adapted to oxygen-poor conditions, adding another layer of consumers and recyclers to the cave's economy. In a world that should be dead, even the single-celled eukaryotes have found workable roles by narrowing their metabolism to match local reality. That matters because it means the cave's resilience is not carried by one heroic layer of life. It is distributed across many scales. The predators make the same point from the other end of the food web. According to the Frontiers Review, top predators in the cave include the water scorpion Nepa anophthalma, which waits beneath the water surface for amphipods and isopods, the blind leech Hemopus caeca, which feeds on earthworms, and the flatworm Dendrocolum obstinatum, which feeds on bacteria, worms, or crustaceans. There is also an identified predator-prey relationship between certain nematodes and the endemic copepod Eucyclops gratericythecus. This matters because predation is expensive. It only persists where enough energy flows upward through the lower trophic levels to support hunters. A truly dying ecosystem tends to lose complexity first. Movile Cave has not done that. It still supports predators at multiple levels, which means the cave does not merely allow life to survive at maintenance level. It supports enough ongoing production for food chains to remain active. In practical terms, survival there includes being eaten, which is not perhaps the most comforting criterion for ecological success, but it is a decisive one. There is also an energy story in the very structure of the cave. Because the most productive zones are concentrated at surfaces where chemistry changes abruptly, the ecosystem can be surprisingly efficient. Thick microbial pellicles and biofilms are both food and habitat, and animals gather around those hotspots rather than spreading thinly through barren space. That means biomass is clustered where it is most useful. In a sunnier system, productivity may be spread over broad plant cover or suspended in plankton-rich water. In Movile, it is focused into films and mats that support dense assemblages of meiofauna. UNESCO notes that the microbial pellicle in the air bells is the key element of the ecosystem, functioning as the place of primary production and as habitat and food for various invertebrates. This concentration helps explain how the cave can support so many specialized organisms in such a restricted space. Survival is easier when food is localized at interfaces rather than diluted everywhere and nowhere. Another reason the cave does not collapse is that its harshness is stable. Surface ecosystems often deal with changing weather, variable temperatures, floods, droughts, and seasonal productivity swings. Movile Cave is warm, humid, and chemically unusual in a much more constant way. That stability does not make the place gentle, but it does make it predictable, and predictability is something evolution can work with. Organisms can become tightly specialized when the environment keeps asking the same questions for a very long time. The cave's oxygen remains low, its sulfide remains present, its light remains absent, and its food base remains microbial. The cost of such specialization is obvious. Species become vulnerable to disturbance and often cannot survive elsewhere. The benefit is equally clear. Over enough generations, organisms can become very good at life in one narrow setting. Survival in Movile is not based on broad flexibility. It is based on deep fit between organism and environment. What makes the cave especially striking is that this fit seems to extend beyond the cave proper, into the wider sulfidic aquifer. The Frontiers Review notes that several stygobionts known from Movile Cave are also present in the associated sulfidic groundwater system in the Mangalia area, including Niphagus dankowi, Eucyclops gratericythecus, and a species of Pseudocandona. That means the cave is not simply one miraculous chamber where life clings on against all odds. It is the accessible window into a broader hidden habitat where survival strategies for sulfide and hypoxia have been tested repeatedly. This wider distribution also helps explain why the system has had time to generate such high endemism and such layered ecological structure. The organisms are not necessarily boxed into one tiny room. Some belong to a larger subterranean province shaped by the same chemistry. A world that should be dead turns out on closer inspection to have neighbourhoods. There is still, however, no reason to romanticize how difficult the place is. The same Frontiers Review stresses that there remains a fundamental lack of studies addressing the tolerance of these extremophile stygobitic metazoans to multiple extremes at once, and that our understanding of their response to interacting stresses is still incomplete. That is worth saying plainly because Movile Cave can sometimes sound too neat in retelling, as though all the answers have been settled and every species has a labelled strategy. They have not, and it does not. The cave is full of organisms that clearly survive hydrogen sulfide, chronic hypoxia, darkness, and a narrow food base. But the detailed physiological mechanisms are still being worked out. That uncertainty does not weaken the story. It strengthens it. It means the cave is not just a solved curiosity. It remains an active question about the boundaries of animal life and the many possible ways those boundaries can be pushed. What survival looks like there, then, is not one grand adaptation, but a layered one. It is microbial flexibility in sulfur, nitrogen, and methane cycling. It is animals staying close to the right interfaces. It is morphological revision over long timescales, with eyes lost, pigment reduced, and appendages elongated. It may be detoxification, sequestration, or bacterial symbiosis. It is food webs concentrated around biofilms rather than forests or plankton blooms. It is top predators still functioning because lower trophic levels remain productive enough to sustain them. And perhaps above all, it is the simple fact that the cave's conditions, although extreme, are reliable. Life in Movile does not win by escaping the environment, it wins by matching it. That is why the cave is so useful scientifically. It shows that worlds which look unlivable from the outside may only be unlivable for the wrong kinds of organisms. Once the right organisms evolve, the world stops being impossible and starts being home. So when we say this is a world that should be dead, what we really mean is that it violates the expectations of surface life. We expect sunlight, fresh air, oxygen-rich water, and food chains that begin with green things. Movile replaces all of that with sulfide, methane, nitrate, microbial veils, low oxygen, and animals that have been revised by millions of years underground. The result is not death, but a different version of success. It is a success measured in persistence, fit, and the ability to keep energy moving through the dark. And once you accept that, the cave starts to say something larger than itself. Because a place like this does not only tell us how its own residents survive, it also changes the kinds of places we have to take seriously when we ask where life on Earth can exist, and where it might manage to exist elsewhere too. By the time you reach this point in the story, Movile Cave has already done something rather useful to the imagination. It has taken several assumptions that feel ordinary on the surface and quietly broken them one by one. Sunlight, it turns out, is not strictly necessary for a productive ecosystem. Fresh air is not universal. Water that would make us deeply uneasy can still support a food web. Isolation does not always end in sterility. So when people ask what Movile Cave reveals about life on Earth and beyond, the first answer is not that it gives us a tidy prediction about aliens. It does something subtler and more important. It widens the definition of what counts as habitable. Movile is described by UNESCO as the first discovered terrestrial self-sustained ecosystem, dependent on chemoautotrophically fixed carbon, and the 2021 Review in Diversity likewise treats it as the first known subterranean ecosystem on land sustained entirely by chemosynthetic primary production. That alone is enough to change the conversation. For most of human history, life and sunlight have seemed so closely linked that it was easy to mistake one for the condition of the other. That was never entirely true, of course. Deep-sea hydrothermal vent communities had already shown that life could flourish in darkness by using chemical energy rather than solar energy. NASA's Astrobiology material on hydrothermal vents emphasizes exactly that point. These are dark places where sunlight does not reach, yet life persists because chemical disequilibria provide usable energy. Movile Cave matters because it brought that logic onto land and into a subterranean groundwater system. It demonstrated that a terrestrial ecosystem could also run on chemical energy from below rather than light from above. The difference is not trivial. It means life without sunlight is not an ocean floor special case. It is a broader biological possibility. That broader possibility is exactly why astrobiologists pay attention to places like Movile. The cave does not show that life is common elsewhere, and it certainly does not let us skip over the very difficult question of how life begins. But it does show that once life exists, it can persist in environments that look hopeless if you judge them by surface standards alone. Movile's ecosystem is sustained by sulfur oxidation, methane oxidation, and nitrification, with microorganisms fixing carbon dioxide into biomass in complete darkness. Reviews of the cave's microbiology and metagenomic work describe Movile as a chemolithotrophically driven system powered by sulfur, methane, and nitrogen chemistry. For astrobiology, that is a very important lesson. The key requirement is not sunlight as such, but access to energy gradients, liquid water, and usable chemistry over long periods. That is why Europa appears so often in these discussions. NASA's Europa Clipper materials say clearly that while life on Earth is powered mainly by the sun, Europa's energy input might come from surface chemistry and water rock interactions on the seafloor, with warm rock potentially supplying hydrogen and other chemicals to the subsurface ocean. NASA's broader Europa overview frames the question similarly. Life needs energy, certain chemical compounds, and liquid water, and Europa appears to have those ingredients in some form. Movile Cave does not resemble Europa in every practical detail, and one should be very careful not to pretend that a limestone cave in Romania is a miniature moon. But as an existence proof for chemically fueled life in darkness, it is enormously helpful. It tells us that a sunless ecosystem is not automatically a contradiction. Enceladus raises a related but slightly different kind of excitement. NASA reports that Cassini found evidence for hydrothermal activity in Enceladus, and later detected complex organic molecules associated with material from its subsurface ocean. NASA also notes that these results strengthen the case that Enceladus hosts conditions suitable for life. On top of that, a 2023 Nature paper reported phosphates in Enceladus plume particles, suggesting phosphorus is readily available in the Moon's ocean, while an earlier NASA-supported modelling study argued that dissolved phosphorus should be relatively abundant there. If you step back from the details, the pattern is striking. Water, chemical energy from water rock interaction, organics, and at least one key bioessential element are all on the table. Movile Cave does not tell us that Enceladus is alive. What it does say is that if life ever got started in a dark, watery, chemically active environment, it would not need sunshine to keep going. Mars enters the conversation from a slightly different angle. NASA Astrobiology material notes that ancient Mars had the ingredients for life, as well as energy sources that may have included solar, geothermal and chemical energy, and plenty of water. Another NASA astrobiology source on the biological potential of Mars argues that chemolithoautotrophic reactions in the subsurface could provide metabolic energy there. That does not mean present-day Mars is secretly full of hidden cave ecosystems waiting for us to say hello. It means that once you stop insisting on sunlight as the main power source, the Martian subsurface becomes more interesting. Earth cave research is now explicitly discussed in the astrobiology literature as relevant to Martian subsurface habitability, biosignature preservation, and microbial adaptation. Movile Cave contributes to that larger thought process by showing what long-term, chemically driven survival can look like underground. One of the cave's biggest lessons is therefore methodological rather than dramatic. It teaches scientists what kinds of questions to ask. Instead of asking only is there sunlight, or is the surface comfortable, it encourages a different checklist. Is there liquid water somewhere? Is there long-term chemical disequilibrium that organisms could exploit? Are there interfaces where oxidants and reductants meet? Could a habitat remain stable enough for adaptation and evolution over geological time? Movile scores highly on exactly those questions. Its productivity is concentrated at redox interfaces, where oxygen, however limited, meets reduced compounds like hydrogen sulfide and methane. The 2023 ISME journal paper on cave theovulum makes that especially vivid by showing how a dominant sulfur bacterium thrives right at the water surface under extremely sharp chemical gradients. For life detection science, that is a useful reminder that the most interesting places may be boundaries, not open expanses. It also sharpens the way we think about biosignatures. A place like Movile is not important only because living organisms are there now. It matters because those organisms alter their surroundings in persistent ways. They produce biofilms, change sulfur and nitrogen chemistry, influence mineral formation, and leave behind patterns that can in principle be measured. Work across cave astrobiology increasingly treats caves as places where biosignatures may be preserved or easier to interpret than in harsher open environments. A 2025 review on Earth caves as Martian subsurface proxies highlights exactly this point, noting their value for understanding microbial survival strategies and biosignature preservation relevant to Mars. Movile Cave is not a perfect Mars analogue, but it strengthens the general case that subsurface environments can preserve both life and the traces life leaves in chemistry and mineralogy. There is another lesson, and it has to do with scale. When people imagine life elsewhere, they often imagine either something grand and obvious or nothing at all. Movile Cave argues for a middle possibility. Life may be local, hidden, chemically constrained, and easy to miss if you are searching for the wrong signs. The cave's entire productive base can be concentrated in microbial veils and films on dark water, with animals gathered around those interfaces. There are no trees, no blooms visible from orbit, no convenient signal saying ecosystem here. If a similar logic applied elsewhere, especially underground or beneath the ice, we might be looking not for a planet-wide spectacle, but for scattered habitable pockets where chemistry and water meet in the right way. That is an inference rather than a direct observation, but it is strongly supported by how Movile itself functions. Its hiddenness is part of its scientific value. At the same time, Movile is useful precisely because it sets limits on our enthusiasm. It does not prove that life is easy to start. It does not show that every chemically interesting world is inhabited. It does not even imply that every dark, wet environment on Earth can sustain a complex food web. Movile works because several conditions come together at once. A continuous supply of reduced chemicals, liquid water, stable long-term isolation, and microbial metabolisms capable of exploiting the gradients available. NASA's astrobiology strategy materials emphasize that habitability is a systems question, not a single ingredient question, and that is exactly how Movile should be read. It is not a magic cave that turns poison into inevitability. It is an example of a narrow but durable fit between environment and biology. Beyond Earth, that is encouraging, but only in a careful way. What the cave also reveals about Earth is that our own planet still contains forms of habitability we are not instinctively good at recognizing. We are surface creatures with a strong bias toward greenery, oxygen, and weather. Movile reminds us that Earth's biosphere includes dark, chemically powered niches that remain easy to underestimate. The 2023 review on Movile microbial ecosystems emphasizes how microbes there adapt to environmental opportunities in energy and nutrients, and the earlier microbiology review notes that many cave invertebrates are isotopically lighter in carbon and nitrogen than surface organisms, consistent with nutrition derived from chemoautotrophic primary producers within the cave. In other words, even on our own planet, life can arrange itself along routes that feel unfamiliar until we look closely. That makes Earth a better teacher than we sometimes allow. Before we speculate too grandly about alien biospheres, it helps to notice how many versions of normal life here never asked our permission to exist. There is a philosophical consequence to that, though I will try not to become unbearable about it. Movile Cave weakens the old habit of treating the surface world as the standard form of life and everything else as a strange exception. Once you have a terrestrial cave system, in which sulfur oxidizing, methane oxidizing, and nitrifying microbes build a food web that supports endemic predators, then the surface begins to look less like the model and more like one very successful habitat among several. NASA's Astrobiology overview frames the field partly around the search for habitable planets and the identification of conditions that support life through time. Movile contributes to that conversation by reminding us that life's requirements can be met in ways that are not obvious from daylight experience. It is a correction in perspective. The universe may not owe us forests. It may offer veils of bacteria on dark water instead. Another reason the cave matters is that it joins the question of habitability to the question of patience. A chemically powered habitat is not especially interesting if it flickers into existence and disappears before adaptation can do much with it. Movile, by contrast, appears to have remained sufficiently stable over millions of years for endemic lineages to evolve and diversify. That matters for the world's beyond Earth discussion because it draws attention to persistence, not just ingredients. Water, energy, and chemistry matter, but time matters too. Europa, Enceladus, and the Martian subsurface are scientifically compelling, not only because they may once have had habitable conditions, but because some of those conditions may have persisted or may still persist over long intervals. Movile Cave demonstrates what long duration can do once a niche becomes workable. It allows adaptation to become deep rather than temporary. There is also a quieter astrobiological lesson in what Movile does not have. It does not need large plants, oxygen-rich skies, or a constant rain of organic debris from the surface. It does not need seasons in the way a forest does. It does not need a visible biosphere. Its most important life processes are small-scale, microbial, and easy to miss. That is a healthy warning against cinematic expectations. If life exists elsewhere in our solar system, it may not arrive as anything we would dignify with a proper entrance. It may be microbial, chemically specialized and concentrated in inaccessible places. The NASA report about possible life signs surviving just beneath the surface of Europa and Enceladus ice is interesting for exactly that reason. Even if life were present there, what we might actually find first could be molecular traces, not creatures. Movile helps train the imagination for that kind of modesty. And yet the cave is not a story of smallness in the dismissive sense. The ecological principle it demonstrates is large. Life can occupy an environment that appears chemically punitive, sealed off, and sunless, provided there is liquid water, usable redox chemistry, and enough continuity for biology to settle in and refine itself. That is not a narrow curiosity. It is one of the more consequential facts we have about habitability. The cave's microbiology, food web, and long isolation combine into a single message. Biology is opportunistic in a very patient way. It does not insist on landscapes that appeal to mammals. It only asks that physics and chemistry leave enough room for metabolism to get started and continue. Movile Cave, in that sense, is less a Romanian oddity than a rehearsal for better questions. So what does Movile reveal about life on Earth and beyond? It reveals that Earth still contains hidden models of living that broaden our search image for the universe. It reveals that darkness is not the same as lifelessness, that chemical energy can substitute for sunlight, that long-term isolation does not always mean collapse, and that habitable environments may be far more local, buried, and easily overlooked than surface intuition suggests. It tells us to look for interfaces, gradients, persistence, and chemical imbalance rather than for scenery that flatters our habits. And perhaps just as importantly, it tells us to be modest. We do not yet know whether Europa's ocean, Enceladus's sea, or the Martian subsurface have ever hosted life. But we do know, thanks in part to places like Movile, that the universe has more than one way to keep an ecosystem going once the right pieces are in place. Which leaves us, quite gently, with the deeper question beneath all the chemistry and all the caves, what it means for a world to remain hidden for so long, and what sort of quiet truth lives in a place that carried on without witness. And so we come to the part of the story that is harder to measure than oxygen levels, sulfur concentrations, or the length of a cave passage. By now we know the practical facts. We know that Movile Cave lies near Mangalia in southeastern Romania, that it was discovered in 1986, and that it opens into a sealed subterranean ecosystem associated with a sulfidic aquifer. We know that sunlight does not reach it, that its food web is built by chemosynthetic microorganisms using compounds like hydrogen sulfide, methane and ammonium, and that its endemic invertebrates have spent immense stretches of time adapting to darkness, low oxygen, and chemical conditions that would make most surface animals turn around immediately and write a strongly worded complaint. We know too that the cave and its associated ecosystem are thought to have been isolated from the surface for roughly 5.5 million years. Those are the details that make the place scientifically extraordinary. But there is also another question sitting quietly behind them. What does it mean exactly that a whole living world could remain sealed away for so long, carrying on in the dark while the rest of Earth changed above it? The first answer, perhaps, is that the planet is less available to us than we sometimes imagine. Human beings are very good at mistaking awareness for ownership. Once a place is mapped, photographed, sampled, and given a proper label, we begin to feel that it has entered the known world in some final sense, as though knowledge were a kind of administrative annexation. But Movile Cave spent millions of years not caring whether it had been entered into our records. It was there all the same. While climates shifted, coastlines moved, species appeared and vanished, and eventually our own kind built cities, calendars and laboratories. This cave went on running a chemical economy of life in complete darkness. Its microbes kept fixing carbon. Its invertebrates kept feeding, hunting, molting, reproducing and dying. It had no need of witnesses. That can feel oddly humbling in a very healthy way. Not bleak, exactly. Just corrective. The Earth is not fully arranged around our attention. Some of its most remarkable processes have been taking place perfectly well without us. There is something else in that idea too, something that presses gently against the way we usually tell the story of life. We often tell it as a story of expansion, sunlight, forests, oceans, migration, spectacle, colour, noise, and visibility. We talk about life as if it naturally wants to spread out into the open and announce itself. Movile Cave offers a very different image. Here is life that became more itself by going inward, life that persisted not by joining the broad green surface world, but by narrowing into a place with no day and no night, no seasons worth speaking of, and no audience at all. It did not become large. It did not become beautiful by ordinary standards. It did not produce feathers or flowers or songs. Instead, it specialized. It simplified. It traded color for sensitivity, sight for touch, abundance for fit. That is a useful thing to remember, especially because we humans are often tempted to confuse visibility with importance. A blind water scorpion in a sulfur cave does not look like a grand statement about the nature of life, and yet, in its own quiet way, it is. The cave also changes how we think about time, though perhaps not in the way the clocks on the surface would suggest. 5.5 million years is a number so large that the mind usually gives up and turns it into a vague feeling of very old indeed. But Movile Cave makes that timescale concrete because the time is written into bodies. It is there in the vanished eyes, the lack of pigment, the stretched antennae, the physiological tolerance for sulfide and hypoxia, and the fact that lineages have diverged far enough from their surface relatives to become species of their own. Time in the cave is not just duration, it is accumulated consequence. It is what happens when the same environment keeps asking the same questions for a very long time, and evolution keeps answering them in bone, cuticle, nerve, and metabolism. On the surface, our lives are often organised by quick changes and short urgencies. In Movile Cave, time worked more slowly and more thoroughly. It did not rush, it revised. That sort of revision also says something interesting about survival. We often speak of survival as though it were a grim holding action, a matter of enduring until conditions improve. But the cave's residents are not waiting for better weather. There will be no sunrise for them, No return to fresh air, no sudden improvement in ventilation, no kindly tree root pushing down a snack from above. Their world has been chemically difficult and physically isolated for longer than our species has existed, and yet the life there is not paused. It is not temporary. It is not keeping a brave face until rescue arrives. It is established. That may be one of the quietest and strongest meanings of the cave. Life can stop treating hardship as an interruption and start treating it as normal. Given enough time, what looks impossible from the outside can become ordinary from within. The organisms of Movile Cave are not heroic in the way we usually like our stories. They are something more convincing. They are fitted. There is, I think, a comfort in that, though perhaps not an obvious one. Not because the cave is cosy, because it quite plainly is not, unless your personal idea of comfort involves bad air, toxic water, and a floating bacterial film doing most of the local food production. But there is comfort in the fact that life is capable of finding workable terms in places we would have dismissed. The surface world can make us rather spoiled in our expectations. We become attached to the idea that real life ought to happen under blue skies, in breathable air, among familiar colours. Movile Cave reminds us that life is not sentimental in that way. It does not demand scenery that pleases us. It asks for gradients, chemistry, water, continuity, and time. If those are present, it gets to work. It may end up producing something pale, blind, and deeply unconcerned with our preferences, but it will have produced something nonetheless. In a world where people often worry that the range of the possible is narrowing, there is something oddly reassuring in being reminded that biology has always had a wider imagination than we do. And then there is the human side of the cave's meaning, which may be the strangest part of all. Because although the cave existed without us, and would have gone on doing so if we had never found it, the moment we did discover it, it changed us a little. Not physically, one hopes, because the cave's atmosphere is not keen on casual participation, but intellectually certainly. It forced a modest expansion of thought. It made us admit that a terrestrial ecosystem could run on chemosynthesis in darkness. It made us take seriously the idea that habitability might exist in hidden, local, chemically powered forms, rather than only in broad sunlit landscapes. It sharpened our questions about where life can persist on Earth and where it might persist elsewhere. The cave did not need us, but by being found it became part of our education. That too is a kind of relationship, though a lopsided one. A sealed world keeps its independence for millions of years, and then one day a rather curious primate opens a shaft into it and learns, with some embarrassment, that the planet has been conducting complicated business without filing the paperwork. Movile also leaves us with a useful warning about how we judge places too quickly. A cave full of hydrogen sulfide, methane, carbon dioxide, near total humidity, and oxygen-poor air looks, at first glance, like the sort of setting best avoided by anything hoping to stay alive. If we had judged it by appearance alone, we would have called it uninhabitable and walked away satisfied with our own good sense. But the cave was not uninhabitable. It was just not habitable for us. That distinction has consequences far beyond one Romanian cave. It changes the way we think about the deep ocean, the subsurface, the hidden aquifers, the buried ice worlds, the places without sunlight, and perhaps even the parts of our own lives that look barren at first glance. Some environments are not empty, they are simply not speaking our language. Movile Cave asks for a slower kind of attention, the kind that does not confuse unfamiliar conditions with the absence of possibility. There is another layer of meaning in the fact that the cave is protected so strictly. Access is limited, rightly, because a place so isolated and chemically balanced can be altered by something as ordinary as human presence. Our warmth, our breath, our microbes, our clumsy admiration, all of it can become disturbance. That too feels symbolic in a rather plain and sensible way. Some things are best understood without being turned into spectacles. Not every marvel improves by becoming accessible. Not every wonder should be lit, ticketed, and given a gift shop with a mildly unfortunate mug design. The cave seems to resist that fate by its very nature. It remains hidden not because we fail to notice it, but because even after noticing it, we must mostly leave it alone. There is dignity in that arrangement. A remarkable place retains the right to remain difficult, selective, and partly beyond our grasp. We get to learn from it, but not to absorb it completely into the ordinary flow of use and entertainment. That may be why the cave lingers in the mind long after the chemistry has been explained. Facts alone do not usually produce that effect. The numbers are impressive, yes. The sulfur bacteria are fascinating, the endemic fauna is extraordinary. But what really stays with you is the feeling of a separate tempo of existence. While the world above concerned itself with weather, daylight, history, and eventually human noise, this place continued in another register altogether. The cave was not frozen. It was active. But its activity belonged to a slower and more local rhythm, one made of films on dark water, blind predators, chemical gradients, and long stretches of uninterrupted adaptation. In a culture that tends to equate meaning with speed, visibility, and scale, there is something quietly corrective about a world whose significance lies in exactly the opposite qualities: small, hidden, slow, chemically strange, very nearly ignored, and yet entirely real. It is also hard not to feel that Movile Cave says something about endurance without ever becoming sentimental about it. We humans are fond of endurance stories that end in triumph, revelation, or at least a neat lesson suitable for a poster. The cave offers no such tidy arrangement. Its life did not endure in order to be admired later. It endured because the conditions allowed it to, and because adaptation kept working on what was there. That makes the story less romantic, perhaps, but also more convincing. The world does not always arrange itself into narratives designed to comfort us. Sometimes it simply demonstrates, matter-of-factly, that persistence is possible under conditions we would have misread. There is no speech at the end of that, no swelling music, just a cave, some bacteria, a centipede, a few amphipods, a great deal of sulfide, and millions of years of evidence that life is often more practical than poetic, which, in its own way, is rather comforting too. And perhaps that is where the quiet meaning of a world sealed away in time finally rests. Not in some grand mystical claim that the cave contains a secret moral for humanity, because caves are under no obligation to provide morals, and Movile in particular seems unlikely to indulge us. Its meaning is simpler and stronger than that. It reminds us that reality is usually wider than our habits of attention, that life can occupy hidden margins for unimaginable spans of time, that the earth contains rooms we did not know were there, running versions of existence we would not have guessed. That time can transform not only landscapes and species, but our own ideas of what should be possible, and that there are places where the proper response is not conquest, not even full understanding perhaps, but a quieter kind of respect. So here we are at the end of this descent, a little farther along than when we began, and perhaps with a slightly different sense of what the planet is capable of keeping to itself. We started with a cave beneath Romania, sealed away from sunlight, thick with sulfur, strange air and strange life. Along the way, it became something larger, a lesson in hidden ecosystems, in chemical patience, in adaptation without spectacle, and in the fact that the world does not become less alive where it becomes less familiar. Sometimes it becomes more revealing there. If you found any calm in this journey, any curiosity, or simply a good place to let your thoughts slow down for a while, I'd be grateful for a like, perhaps a subscription, and maybe the sharing of this quiet corner with someone else who might enjoy drifting off inside a scientific mystery. And before you settle in fully for the night, I'd love to know, just as at the beginning, where are you listening from right now, and what sort of hour has gathered around you there? It is a funny thing, really. We spend our lives keeping time, checking it, saving it, losing it, and yet somewhere beneath the surface of one ordinary part of the world, a hidden ecosystem went on for millions of years without asking the clock what it thought. Sleep well, wherever you are.